Good morning, everyone. Welcome to the Solid State Tech Talk of EMIRI. We are still accumulating the number of participants, so we will start not at 9:30 sharp, but in 1 or 2 minutes, just to make sure that people are having the chance to join the session. So what we will do is that in 1 minute, we will be starting. And as soon as we have a certain amount of people, I will start the flow of presentations. We are only at 60 people. We are expecting about 300 people. So there's still some way to go before we are reaching a certain amount of people before we start the program. For those who are already on the call, what we will do is that you have, for those of you who are accustomed to using Zoom, we have the Q&A function that you see on the bottom of your screen. The Q&A will be typically used if you have any questions that you want to ask to the presenters of the morning. Please do put your questions in the Q&A. Just make sure that you are all muted in order to not create discomfort for the presenters. And that should be a good session. If there's anything else than a question, of course, the chat is also a place where you can put messages. But any questions that are specific of the presentations, we would like you to put them in the Q&A just to make sure that we can see all the questions and we can address them to the speakers. So what I will do is that I will actually start the presentation of the morning, and we will get a few people joining the call as we progress. So good morning, everyone. This is a quite interesting morning that we have prepared for you. This is an event that we are organizing with EMIRI, with BEPA, as well as with Batteries Europe, the think tank, I would say, of the European Commission on batteries. And the purpose today is to give you, in one morning and an afternoon session, a broad overview of the field of solid-state batteries. That is very important, of course, if you follow the developments. Quickly, morning session, the purpose is actually to give you a feeling of how important solid-state batteries are on the roadmap of many companies. Second point is also to highlight the challenges that we still have ahead. This is not a mature technology. This is a technology in the making. So a lot of R&D is still needed to go along. And last point that we want to give you a feel of is the need to collaborate up and down the value chain in order to make this a successful technology development. So in the morning, you have presentation by companies, with, of course, an introduction on the business side from Arthur Delittle, and on the technology side from Fraunhofer ISI, and afterwards a couple of presentations by companies, upstream, midstream, and downstream of the value chain of batteries. In the afternoon session, what we have is, in a couple of hours, a nice overview of some European projects that are either running for some time or started, and that will give you a nice landscape of what's happening in Europe, funded with European funds. And that would be it for a very short introduction to the morning. If there are any questions on the logistics and how we are doing this, please do not hesitate to put them in the chat, and we keep the Q&A for the questions to the speakers. So without further ado, I will now give the floor to Philippe and Walter. Philippe, you know very well, Philippe is the general manager for EMIRI, which is the Energy Materials Industrial Research Initiative, but he has a double hat, I would say. He's also the Secretary General of BEPA, which is the association running the partnership on batteries. And afterwards, we will have Walter IJzermans, who is the executive director of the same organization, BEPA. So Philippe, I'm happy to share the floor with you.
Thank you very much, Fabrice, and good morning, everyone. I'm Philippe Jacques, so the Managing Director of EMIRI, and I will focus quickly on a very short introduction of EMIRI, and I will let it to Walter to introduce BEPA. So first of all, I would like to thank all of you for being there, and I'm very happy to have been able to organize such an important event on RNI activities for solid-state batteries in close coordination with BEPA and Batteries Europe. So what EMIRI is about, it's an association, European association, which is focused on advanced materials for energy and mobility. And really our aim is to address all the relevant topics which really will contribute to developing more performant materials that really will address the key challenges that Europe is facing, both on a climate point of view, I would say, also addressing the competitiveness of the industry, and also really making sure that the solutions we are developing are always more sustainable for the benefit of all the citizens. So that's in a nutshell really our core mission. So we are covering not only advanced materials for batteries, but we are covering advanced materials for all the different sectors of renewable energy, energy storage, and mobility. What we do basically is to work to align the RNI policies with the industrial strategy. And in the field of batteries, I think there is a great a great example of how these policies, when they are aligned, really benefit to the industry and to the research community, and at the end to the European Union. So we are working in close coordination with the different initiatives that are ongoing in the different fields of batteries, hydrogen, low carbon industries, for example, and with a particular focus on RNI activities, which means a particular focus on European partnership. So that's why we have developed this strong collaboration with Bat4EU, with BEPA and with Batteries Europe. And how we position ourselves is really to consider that we are a little bit like the antechamber, really to define the priorities that will really be structured and prioritized in the different fora which are feeding really the RNI policies in the different partnerships. So if I try to summarize in 2 minutes the RNI ecosystem for batteries, and this one is a joint work with Walter that will come after me. But so what we and also I think we have to give credit to this to PDI, VDE, who also helped to structure this landscape. So if we consider that innovation is crossing the field of policies, business, and education, you see that we have the main stakeholders and initiatives which are active in the ecosystem, which that I guess you all know very well. Batteries Europe, which is the think tank, BEPA, which is the private side association which is involved in the Bat4EU partnership. We have Battery 2030+, which is the network gathering the academic world, really looking on disruptive technologies and really focused more on long-term research needs. And we have on the other side, on the business side, we have the two IPCEIs on batteries, which are really bridging research innovation with really the industrial activities. And we are really working hard to structure this in the most efficient way. And EMIRI is contributing as a, let's say, upstream really to provide input on these Batteries Europe and BEPA joint working groups that most of you, I guess, know very well, which are really dedicated to developing the roadmaps and at the end developing the work programs for the partnership under Horizon Europe. So I don't want to make it too complex and too long on this one, but I think it's important to understand really what is the specific role and positioning of each of the co-organizers of today. So you see, we are totally aligned and we are totally, let's say, committed to achieve the same goals with, of course, a broader and a much more important focus on advanced materials on EMIRI side, while BEPA and Batteries Europe are covering the different segments of the battery value chain. I would like just to take 2 minutes, if you allow me, Fabrice, just to also to promote another initiative that we are heavily involved in on EMIRI side, which is the Advanced Materials 2030 initiative. In 2 words, the objective here is to build hopefully a new European partnership that would be a transversal one on advanced materials. So really addressing the big challenges that you all know and which are supported by different policies at the EU level. And really what we want to do is to mobilize and to engage the broadest possible community on advanced materials, really to elaborate the strategic agenda that will feed the next strategic plan for Horizon Europe for the years 25-27. So it's now that we need you to contribute to this. So it's definitively not focused on batteries. It's much broader, even not focused on energy. It's really trying to capture all the relevant topics and tools that really will benefit to the materials community and will help to accelerate the development of materials for the benefit of all the application sectors where materials are key enablers in developing the improved technologies. So if you are interested to join, you can have a look at the AMI2030.eu website, and you have the possibility to join the initiative and to join the working group, which are currently working on this strategic agenda. And if you would, by chance, if you are free tomorrow, we are organizing a workshop that will also provide you with more information. This workshop will be held physically in Mons in Belgium, but it will be also available online. So don't hesitate, have a look on the AMI2030.eu website and don't hesitate to register if you have a few hours available tomorrow afternoon. And I will stop here. Thank you very much, Fabrice.
Indeed, AMI or EMI, depending on how you pronounce it, is the place to be if you are into materials. So follow it and register and join it. I will now give the floor for a couple of minutes to Walter Heisermans from BEPA before we move to the presentation by Arthur De Rieter. So Walter, you have the floor.
Yeah. Thank you, Fabrice. I will keep it short, given a look at the time as well. We need to focus on the content. That's what makes this webinar great. I want to thank EMIRI for organizing this because it comes at a pivotal moment as well for us within the partnership. We have had some 2 rounds of calls already out, the calls of 2021 and 2022, some of which lead to projects that will be presented later on. We have worked in the past 2 years on the calls of 23 and 24, but right now we are maybe taking a little bit of step back and looking at where we need to go into the future. And the way we are doing that is that we're working together with Batteries Europe in joint working groups, and we're working on dedicated roadmaps for the specific sectors. There's one going to be a part on it on advanced materials as well, and that work will be done between now and May. And then after May, between May and September, we'll start looking at how this technology roadmap, so basically how we get from where we are now to where we want to be in 2030, 2035, etc., will be need to be addressed in the Horizon Europe working programs. So it's quite a pivotal time where we can actually decide on the priorities, see what the key challenges are that we need to address, both in general in Europe and specifically in the Horizon Europe work program. So I will post a link in the chat as well for those who are not yet joining the working groups of Batteries Europe and BEPA. Feel free to join. Fabrice is also very active as the industry chair there, so you'll see a lot of familiar faces. But it's really this is the moment to contribute to the work that's being done within the partnership. And with that, I'll leave the floor to
Walter. So
actual.
If you are into batteries, this is also another place to be. So do not hesitate to join BEPA and follow as much as possible the work, great work that is done by Philip and Walter there. So another place for you to start looking at if you are not already active in it. I will now start, I would say, the content session, as we would say. So we will start with a presentation by Rodrigo from Navarro from Arthur de Little. Rodrigo is a principal at Arthur de Little Amsterdam, but he has also a very long experience in industrial technology intensive areas related to energy. He's been before at DSM and NXP and Philips, also including some materials venture activities. So basically, the good thing is that he has this very broad understanding of the industrial world, coupled with a very strong consulting experience. So we are very thrilled to have you, Rodrigo, and the floor is on you, is yours.
Yeah, no, thank you, Fabrice, and well, good morning, everybody. So thank you for the introduction as well. So indeed, just to kind of introduce myself. So I've been kind of active pretty much like my whole professional life on batteries, renewables, emerging technologies, growth areas in general, for corporations, and for the past several years as a strategy consultant, of course, for ADL. So I think, as Fabrice mentioned, I have like more than 10 years of actual industrial experience in batteries. And my goal with this talk is really to try to bring all the holistic view that I'm seeing on the market based on all the projects that we have been working on for the past several years in the marketplace, and give some hints or give some angles to this broader community. I'm sure that there will be lots of presentations, much more technology focused during the course of the day. I'm trying to keep the level a little bit higher to give the broader picture, basically. Just to introduce ADL a little bit in half a minute. Basically, we have been active on areas related to the green energy transition for in a variety of topics. And here I just depict a few of them. Besides the battery core and lithium-ion technologies, we are active in many different fields, including chemistry, solar, hydrogen, and all the different topics associated with EV and electric transition as well. And we have kind of an extensive experience across the globe with different tier one, actually, corporate clients and emerging companies as well, offering a variety of actually projects and doing a variety of projects across the value chain. And that's where some of these hints of this talk today come from. And I'm bringing a few of those to you guys, and we actually publish quite a few of those from time to time and frequently. So coming back to the battery chain, I basically kind of selected here a few of those trends that we see on the overall battery value chain that I think are quite linked and potentially significant for the broader solid state trend as well. So I'm going to go quickly through each of those three major sectors that I broke that are related to the solid state area, especially. One of them is the raw materials and recycling trends, which are influenced by this need for localization that I'm sure that several of you have heard and are noticing in the industry as well. And on the other extreme, the growth of recycling as well, which is another key trend, let's say, and the whole industry in Europe is definitely moving ahead in this direction, and not only in Europe, of course. Then the second one, in terms of chemistry and technology, where there are quite a few factors associated with new drivers that are taking place associated with the choice for technologies that are being made in the field. And then the third one is related to applications, where, well, as you are aware as well, there is like obviously an increasing amount of applications that are popping up associated with batteries. And I wanted to highlight a couple of points with a few of those in this talk. So starting with the raw materials and recycling, I mean, I think I don't need to tell probably to many of you that that's definitely one of the most pressing issues that on a global level people have been paying attention to and acting, especially at the government level, trying to reduce the dependence on certain geographies and to actually really deglobalize, let me put it that way, the supply chain associated with the batteries. I wanted to kind of briefly, I mean, there's lots of different predictions and forecasts and statistics about the use of metals. I just wanted to kind of emphasize one point. I mean, this is definitely something that the solid state industry will have to start paying more attention to. And the second thing is that as we have done an assessment, I actually do believe that to a large extent, complete self-sufficiency, right, is not going to happen actually at any geography level, including also Europe across the globe. So the industry has to balance a little bit a certain level of self-sufficiency with the actions associated with guaranteeing at least some level of localization of the value chain. And particularly in Europe, just if I want to, there are quite a few trends and vectors that the European Commission and the governments are trying to achieve, right? So they are trying to build this self-sufficiency here and on the raw material side. On the other extreme, on the recycling side, actually all the actions are towards trying to build an EU ecosystem from almost from scratch, let me put it that way. And then all of that has consequences across the value chain, right? And what we see in Europe is that Europe having a very strong set of actually companies that are active in the materials field, companies like Umicore, like BASF, like Solvay. So those companies are taking action towards more vertical integration, actually trying to basically make sure that they are more active on recycling. And there is the build up basically obviously of the whole OEM and battery makers in Europe in terms of making sure that there is production in Europe as well, as you probably all have heard about. In terms of the link to recycling, obviously the regulation in the European community associated with the extended producer responsibility also has an impact, especially with the battery makers and the OEMs, and the drive for those to recycle and to guarantee that they are basically targeting recycling. To touch the importance of the raw materials and recycling on also across the ocean on the US as well. Some of you might have seen also the recent actions from the US government associated with the Inflation Reduction Act, and that is also something that if you look at all the companies that have been chosen for the 3 billion grants that have been granted recently, basically the current choice that the US government have made are basically companies in the materials part of the value chain, materials/recycling. And I think that is something that tells where the prime priority in terms of the governments are at this point in time. And I think from a solid state perspective, it's important to notice, and I wanted to highlight that, well, for now, at least solid state companies, despite the fact that the US have a significant or has quite a few startups in this field, they have not been yet selected. I think in the as part of the phase 2, let's say for the grant process, I think we expect that the US government will well, it remains to be seen, right, if they are going to select also solid state companies for that, having in mind that several of those companies have recently gone through SPAC process in the US. and so they might have a decent amount of funding, but that is something to kind of be monitoring, that we should monitor going forward, let's say. Now jumping quickly in terms of the technology, I wanted to use kind of the example of cathode innovation just to kind of see, to illustrate how things changed in the past years. And here, what I depict here is basically you see how the new drivers associated with the value chain and innovation across the value chain are changing, right? And you see that most of the innovation right now happening in cathode, they are associated with really kind of improving the environmental footprint. They are associated with making sure that the production across the value chain is minimized to reduce cost and optimize actually the value chain. Examples of that are, for example, the recycling companies that are trying to actually cut some of the steps associated with the metal refining, for example, like Ascent. On the other extreme as well, companies like Umicore, Redwood, and Northvolt that are actually trying to vertically integrate either towards recycling and or in terms of cathode making, right? Like with Redwood also integrating towards cathode making steps. So in general, one thing also that is largely or was largely overseen over the past years when people were mainly focused on the chemistry itself of the cathodes, there is lots of environmental impact to produce cathode materials, like with lots of amounts of sulfuric acid needed, lots of ammonia and etc. Materials. And part of the innovation here, it's also about making sure that this value chain is sustainable and effective from a cost perspective as well. And I think all of this, I think the solid state community has to realize that that will become relevant as well in terms of assessment for the solid state area as well. In terms of the LFP as well, I wanted to give kind of an example of how that is relevant. In terms of there has been a shift towards LFP or in a preference towards LFP chemistry in the past years, as several of you have noticed. And I think I wanted to highlight 2 points. It's clear now that even many of those gigafactories, the transition, let's call it the simple transition, even from an NMC to LFP, it's not straightforward, right? So they actually, several of the gigafactories that we talk to, they expect to struggle in this transition as well. And that is supposed to be a simple transition, right? So again, put into context the solid state shift that is expected to potentially emerge, that is a relevant aspect to take into account. And another aspect is about the CO2 consumption, basically. That is actually something that, as you can see here, this is definitely going to keep being relevant in this field and increasingly so. Now, the other aspect from the technology that I wanted to highlight is the increasing complexity and fragmentation of this field. And I think that is something that what we see is that the industry is becoming just increasingly more complicated. And the lithium-ion technology is continuing to emerge, right? So there is a significant drive towards a non-lithium-based technology like sodium-ion, with several pluses and minuses, and then there is the potential shift towards solid state, right, where it's driven mainly by energy density. And I think, and there are already, as I think I illustrate in this slide as well, there are already many routes basically associated with solid state, and I'm sure that the remaining speakers will talk about several of those in the coming day. And I think the industry has to be a bit has to pay attention to that, because I think that this what I'm saying, like this additional complexity, let's say, especially the automotive sector, for example, they don't want to be dependent on single companies or single technology pathways, right? So one of the advantages of lithium-ion, that's actually, I mean, there are actually many players associated with lithium-ion, and that's actually something good. So it kind of de-risk the supply on the supply side. I think that is something that the solid state players have to try to have a balance between differentiating themselves, but not give the impression to the industry that they are the only way forward as well. And then on this topic of the automotive, on starting to go into the application segmentation, this is kind of is the result of conversations and interviews that we have had with several of the automotive players. And you see that there is this the comparison between even within lithium-ion between LFP and NMC, and what I expect to see here in terms of the impacts to solid state, right? What is clear in a nutshell is that the only real, the key advantage in terms of selling point from solid state at this point in time is largely focused on energy density. And I think at least in the foreseeable future, there would be a negative impact in terms of cost. Is to be proven actually in many of those solid state directions, the environmental impact, if it's a positive or a negative in the end. I think the industry has to be paying attention to recycling. It's to be proven still also the safety, although this is a selling point and lots of the solid state players claim to be a selling point. I think that's a point that still has to be proven. And there is the risk here in terms of supply, right, that I just remained. So the message here is that I think being a bit kind of trying to be a little bit realistic, I do think that this shift, especially on the automotive side, is not a given. And I think that the industry has to pay attention to make sure that these aspects and these attention points that I indicate here are actually covered by the players, and trying to depict a future where, in fact, it's not only energy density that's going to be really the key differentiator aspect. And then to finalize in view of time, and it's very, very short, I wanted to kind of, so based on what I just said, I do believe that across the market, there are lots of the application segments that are going to be a challenge for solid state to start with, including the ones focused on lower cost and longer life cycle, like stationary storage and low end of the automotive market, for example. So definitely solid state players should focus more on the high end. And within that, I do think that, and based on the projects that I have done, I do think that the electric aviation is actually a potential major, should be seen as a potential major target for the solid state industry, given the fact that it's an emerging field which can accept actually a more small scale start from solid state players as well. And that's basically kind of what I'm, in a nutshell, what I'm trying to depict here, that I think within the electric aviation field, there are different sectors, and we have actually done some analysis on that. And we actually found that there are actually some subsegments of the of the electric aviation market, which I depict here as part of the eVTOL and part of the e-aircraft segments, which we think that they have a high eagerness to accept actually this trade-off between having lower life cycles and higher energy density, that we think could be a good starting point for solid state players to target. Yeah, so I think in view of time, that was mainly my 15 minutes. In a nutshell, I think in terms of the raw materials and recycling, I think solid state players, they need to take increasingly into account this holistic view with materials and recycling. I think from a chemistry and technology of choice, I think the key message is the key value proposition for solid state, which was largely focused on energy density, is becoming increasingly of secondary importance in this bigger picture. And it is unclear if this will be enough for enabling this technology shift on the automotive segment. And in terms of the application, I do think that this trade-off energy density and potentially lower life cycle might be a better fit for higher end applications where solid state players can start small and scale up with those markets. That is it. I think I barely covered the 15 minutes, right, Fabrice? I don't know if there is time for.
Thank you, Rodrigo.
We just move on. Thank you very much.
I think that you have clearly shown the complexity of the field and all the issues that we have to tackle. It's not a given, of course, solid state, and there are many question marks that still need to be answered. There's one question that I want to bring to you, and there was another one which is more technical, so maybe this is maybe for another speaker, but you have mentioned all the roadblocks on the way to, I would say, a big adoption of solid state batteries. If you had to give a date, I know it's very dangerous, when do you see a reasonable shift to SSB if all the good conditions are met?
Yeah, no, I think the answer depends on which application segment, right? I've been working on solid state since 2013, and I've seen all these predictions of, oh, it's coming in 5 years, it's coming in 5 years. So it's always like this sliding window. And I do think that obviously for automotive, it is, as I said, it's increasingly complicated, and it's still to be seen if this shift is even really going to happen. To be honest, it will largely depend on some of the factors that I described. I do believe that for the solid state players, they in some of those higher end segments, the shift can come, right, much sooner than for the automotive segment. I think that's kind of my view on that.
Okay, thank you so much, Rodrigo. The presentation will be made available to all. I think that's not going to be a problem for you. If there are any other questions, we can still take questions towards the end of the morning session if we have enough time. So thank you so much, Rodrigo.
Yeah, thank you.
Next speaker on the list, I don't know if I have to present him, but I still give a few words about Thomas Schmalz, that many of you know in the field. But Thomas studied material science and engineering in Germany. Then he did a PhD in organic electronics in 2014. And then he joined the Fraunhofer Institute for Systems and Innovation, that you know under the name EASY. And there, as a senior scientist and project leader, is actively looking at novel technologies and innovations in the field of battery technology. And with Mr. Tillman, is one of the key authors of this very strong roadmap on battery for solid state that you have published not so long ago. And this is what we wanted to do today, is to give you in 20 minutes a nice overview of the Fraunhofer roadmap. So Thomas, you have the floor.
Thank you very much, Fabrice, and yeah, hello to everyone. It's a pleasure to being here and be invited. Thank you very much for that. And I will try my best to give a rough overview over the broad field of solid state batteries in 15 to 20 minutes, which obviously is a challenge because it's a very broad field with a lot of interesting aspects that we could talk about for hours and hours. But let me just start with a bit of context. So as we all know, lithium-ion batteries, the market is growing, and it's growing fast, massively. And a strong driver is electromobility. And what you can see here is a scenario forecast for what we believe the lithium-ion battery demand could be globally in the next years. As you can see, it's still relatively small, and it will increase massively. So we're currently in the phase of a massive expansion of battery production. And this is now all lithium-ion batteries. And so what we did in the course of our study on solid-state batteries is that we tried to estimate on how large the market for solid-state batteries could be in the next years. And we did that by asking experts from industry and academia. And what came out of this little survey was that the solid-state battery market might be still relatively small in the coming years. So the little forecast there was that in 2030 it could be 15 to 50 gigawatt hours per year, and in 2035 40 to 120 gigawatt hours. When you compare that to the overall lithium-ion battery market, that's relatively small. Personally, in the meantime, I believe that it might grow a bit faster. But yeah, maybe later in the discussion round we can talk also a little bit about that. On my next slide, I want to go to a bit more clearer numbers, and that is the publications and patent application numbers. So we made a little publication and patent analysis looking at which countries are actually active in the field. And what we can see is that for the publications, China is actually publishing most on solid state batteries, followed by the US. But Europe is actually also not bad in this context. We also have significantly numbers of SSB related publications. When we look at the patent application numbers, situation is a bit different. The highest numbers are currently in Japan, followed by the US, and increasingly also South Korea and China. The situation in Europe is not so good here, I would say, and also rather stagnating and not increasing compared to other countries that are where the numbers are still increasing. So we possibly should work a bit on that. So now let's look a bit more at the technology side of solid state batteries. So I have a sketch here of a liquid electrolyte lithium-ion battery, and on the right side, a solid state battery, just to show what are the differences. So basically the components are very similar. Only in the solid state battery, you try to get rid of the liquid electrolyte that you have the conventional lithium-ion battery, and you try to remove that with the solid electrolyte. And the separator will then also consist of the solid electrolyte. So looking more closely at the individual components, on the anode side, a big driver for solid state batteries is actually the use of the lithium anode. Because the lithium anodes allow for the highest energy densities on the anode side. But at the same time, it's most challenging because lithium is a quite reactive metal. And there is only little processing knowledge of thin films of lithium metal, and to include that into the production of the batteries is quite challenging. For that reason, people are also working on the silicon anode. That is a bit less complicated and is also ongoing on the liquid electrolyte lithium-ion batteries. So there is a trend towards silicon anodes. They are typically composed of a silicon carbon composite with increasing amounts of silicon in there. Silicon doesn't have as high of an energy density on the anode side compared to lithium, but still significantly higher than graphite carbon anodes. For high power application, one could also think of other cathode anode materials such as LTO. Looking at the cathode active materials, for solid state batteries, they are actually very similar compared to electrolyte lithium-ion batteries. So you have either the medium price, medium performance materials such as LFP or LMFP, increasing amounts of manganese. You have conventional high performance materials such as NMC, NCA, high voltage materials, LMNO. But especially for the high voltage, high potential materials, additional coatings might be required to allow for good compatibility with the solid electrolytes. In the longer term, sulfur might be actually a very interesting candidate when we're looking at high energy densities. But there are quite a bit of technical challenges that still have to be resolved. So the other materials are we see much sooner in the future. So the core of solid state batteries is of course the solid electrolyte, and there we think that the three solid electrolyte classes are the most promising. The first one is the oxide solid electrolytes, second sulfide, and third the polymer solid electrolytes. The oxide solid electrolytes is a big group of materials. Here you can see some examples. They all contain lithium oxide often phosphorus and other metals such as aluminum, titanium, zirconium, so on. They are ceramic materials. They are rather hard and brittle. They show a good electrochemical stability, which is very good. So they have a good compatibility with the lithium metal anode, the anode side, but also with the high potential cathode active materials. A bit problematic can be the brittleness itself. It can be the production aspects, because to have a good mechanically robust ceramic, you would need to sinter them, which requires high temperatures. And the ionic conductivities are actually too low for the all components in the solid state battery, especially for the cathode as a catholyte. Looking at the sulfide solid electrolytes, it's also a broad class of materials where we have a wide choice of specific material. They all contain lithium and sulfur, and most of them also contain phosphorus, and some of them halogens, or yeah, other metals or other components. They show typically a rather high ionic conductivity, which makes them suitable also as a catholyte. A bit problematic for the sulfide solid electrolytes is the compatibility to the lithium metal anode, but also to the high potential cathode active materials, so that additional coatings are required on both sides, basically. Last but not least, polymer solid electrolytes. There are also many different candidates. So the currently used or most used one is PEO, but you have a lot of different polyethers, polyethers, polynitriles, and a lot of emerging polymers that can be used. You need to add salts to make them ionically conductive and other additives. A bit problematic for the polymer electrolytes is the low ionic conductivity at room temperature. But when they are heated up to 50 to 80 degrees, they show quite decent ionic conductivity, so that they can be solid state battery. They show a good chemical compatibility to the lithium metal anode, but not to high potential cathode active materials, which is why currently on polymer SSBs that are actually already on the market, LFP is used. Cathode. So now let's look at some promising cell concepts. So starting again with the oxide electrolyte version. So there, the most promising cell concept will most probably contain a lithium metal anode with a good compatibility then to the solid electrolyte. And on the cathode side, NMC material is most likely to be used. The problem is that the solid oxide electrolyte has a too low ionic conductivity to be used also as catholyte, which is the reason why a gel electrolyte probably used in this concept, which means it's actually not an all solid state battery concept, but rather a hybrid concept. The application for this that is envisaged is in electric cars. Companies that are working on that are Prologium, QuantumScape, and Qingdao, best of our knowledge. And yeah, technical challenges are the low ionic conductivity, but also the processing of thin uniform films of the solid electrolyte separator. For the sulfide electrolyte, we consider two concepts as most promising. They both have NMC material as cathode active material, the sulfide electrolyte as catholyte and as separator. And then one contains the lithium metal anode, the other one the silicon composite anode. And there you also need the sulfide solid electrolyte as anolyte. So the advantage of this concept is that the sulfide solid electrolyte has good enough ionic conductivity to be directly used in all parts of the battery. For the silicon anode version, the advantage is that the processing is very similar to the current processing of the anode materials. Of course, it's not identical because you need to add also the solid electrolyte, but it's similar. But the energy density is a bit lower compared to the lithium metal concept. The applications that we see there is also mainly electric cars. That is a big driver for that. And companies that are working on that are, to the best of our knowledge, Solid Power, CATL, LG, Panasonic, Samsung, SK Innovation, Toyota. Technical challenges for those concepts are the compatibility of the sulfide electrolyte with the NMC and with the lithium metal anode, and the material production in ton scale for the sulfide electrolyte, which especially here in Europe has not been established. Looking at the polymer SSP concept, we look at the commercial concept that is on the market already, that contains a lithium metal anode, a solid polymer electrolyte, and LFP as a cathode, and the polymer electrolyte also as a catholyte. This concept can potentially be rather cheap because the materials are not super costly compared to the other SSP concepts. And another advantage is that it's actually already on the market. So you can see buses driving around with this type of batteries already. On the downside, for this battery, you currently need heating. So you need to constantly heat it up to 50 to 80 degrees. Which of course limits the application scenarios to applications where the batteries are more or less constantly and don't have very long downtimes. Companies that are working on that are Blue Solutions, Ganfeng Lithium, WeLion, Hydro-Québec, Factory Energy. Technical challenges are the low ionic conductivity at room temperature. There is ongoing work, of course, to reduce this temperature by, for example, using different polymers. Another challenge is the limited stability in contact with NMC materials, so high potential cathode active materials, which is also what people are working. So having a very brief look at the production aspects. So the lithium-ion battery production, done by wet processing mostly, and this will of course change, especially when we use a lithium metal anode. But there will be different steps that need to be taken. The cathode side can be still wet processed, but especially for the oxide versions, you need a certain low temperature sintering step as well, and for the separator, then even a high temperature sintering step. So there are certain differences, pronounced difference in the production of solid state batteries. I think I don't have time to go through all the details here. But maybe looking at the cell assembly, in the end, some steps will also not necessary anymore. That is the electrolyte filling and the degassing. And there is the hope that also the formation aging might be shorter for SSP compared to liquid electrolyte batteries. So why are we actually working on solid state batteries? Well, that's because, as Rodrigo already said, the KPIs could be potentially quite a bit improved compared to the current lithium-ion batteries, and especially the energy density, of course, is a big driver for that. We have calculated some let's say theoretical values, assuming certain thicknesses of materials and certain density, what can be reached, assuming, of course, the compatibility between materials. And what we can see is that actually the energy densities could be quite a bit improved compared to the current generation of lithium-ion batteries. The safety could potentially also be higher. There is no liquid, flammable liquid inside. Also, the long-term stability and the lifetime might be improved, but it's a bit too early to say. And this, in the end, could also be a big driver, safety and long-term stability, to boost solid-state batteries. Fast charging, can be implemented in solid-state batteries, but of course at the cost of energy density. So what we have to keep in mind is that if we optimize a battery for one of those KPIs, the other KPIs will suffer from that. So let's
Thomas,
have a quick.
you still have 2 minutes.
2 minutes, okay.
2 minutes. Yeah.
Sorry, I will speed up. This is the roadmap that we drew, and it's a bit complex, too complex to go through everything in detail. But just let's focus on the applications. So what we can see, or what we expect, is that solid-state batteries might come to the market in automotive applications between 2025 and 2030. But rather in a small scale initially. So yeah, my conclusions are that we are currently in a phase of strong market expansion from lithium-ion batteries, and the technical KPIs of liquid electrolyte will improve in the next years as well. So by the time that solid-state batteries will reach the market, they will not be so incredibly better anymore. So the companies speed up a bit and try to push for solid-state batteries to come to the market. We see them first coming to the premium segment because we expect them to initially be more expensive because of the smaller production volumes and new materials required. What we can see currently already is the trend of semi-solid technologies, so hybrid battery technologies, where we have a lot of announcements from battery producers. Looking at the situation in Europe, the R&D level is actually good, but we're lagging behind a little bit in production processes, equipment, pilot production, and industrialization. We need to set up supply chains for the materials of solid-state batteries, and we need actually more funding that is going towards pilot production and production of solid-state batteries. And with that, thank you very much for your attention. Just a little advertisement to what Fabrice already said. We've published this solid-state battery roadmap earlier this year. Here you have the link. It's a document of more than 100 pages. There are a lot more details than I could now tell you in a short time. Thank you very much.
Thank you so much, Thomas. And if you have time for some holiday reading, Christmas holiday reading, I would suggest the roadmap for those of you who are brave enough. That was actually a very strong document. One quick question for you, Thomas, before we move to the next speaker, is when we develop materials for SSB, to which extent do we take into account recyclability? And also to which extent do we take into account the needed scale-up if we move towards including more and more rare earth metals in the composition?
So there is definitely the trend to use materials where we don't have rare earth metals. So some of the sulfide solid electrolytes, you could see germanium or so inside. And this is just also for a cost reason. This will most probably not be used. And then, well, most of the materials that are in the solid electrolytes can then be recycled. So especially the lithium, that is the most important one. But of course, when you design such a battery, you need to think about the recycling as well. And especially the sulfide could also create some trouble with the current processes, the hydro processes for the recycling. But yeah, it has to be considered as well. But we still have some time to optimize the process towards that, because, well, it will take a few years until the batteries are on the road, and then it will take hopefully many years until they come back after their end of life.
Okay, thank you, Thomas. I think it's always important to have a circular approach when we develop materials to not create problems for the others. So this is good that the R&D community is already thinking about it. Thank you so much. So we will move to the next speaker. The speaker is now coming from the industry, and we are starting from the bottom of the value chain, so from the OEM side. We're happy to have Jürgen Ildinger from BMW. He studied electrical engineering in Germany until 2000, and then he did a PhD on electric drive sensors, control and machining designs. After that, he moved to BMW, that we all know very well, where he has been head of cell development and pack design until 20. And ever since, he's now the head of battery and charging research. So that's also including solid state batteries. So we are very happy to have you, Jürgen, to listen to the BMW position on solid state batteries. So the floor is yours.
Thank you, Fabrice, for the very warm welcome words. So I try to share my screen and I will start.
Yes, we see it.
You can see it, oh?
Yes.
Okay, so thank you for even Mr. Schmalz to have this very good introduction in the solid state batteries. So as you mentioned, I'm in charge for the battery research and did this, let's say, overview together with my colleague Peter Lamp, which might be very well known to this community. And I'm more in charge for the battery pack design, so incorporating the, let's say, cell characteristics in somehow a proof of concept on a battery level. And we decided to have even a certain, let's say, amount of discussion on these points, which come to truth if you try to put it in a battery today. So I would start with a summarizing view for the next some minutes. What is most essential for us? So we talked about the, let's say, advantages of the all-solid-state batteries, and we judge it to be really competitive, which of course is also a very important thing to reach. To have it not only in a niche for some technical evaluation or a small, let's say, portion of the portfolio, but also have it, let's say, a really powerful opportunity for future electromobility. So that incorporates the competitiveness and the technical readiness of the concepts. We see that a little bit earlier, but in total, we judge it to take another 10 years to come to that point. So the next point about the solid-state batteries, we look more from the electrolyte side. It was very good explained that there are different opportunities. We judge it to be really an open race because it's not 100% clear in which direction the, let's say, requirement portfolio for this chemistry goes. And so either the one or the other technology might have an advantage. So anyway, it's the key issue to be achieved for all this technology concepts in our eyes is judging about the industrialization potential, which will on the one or other hand show if one of these technologies is having an earlier kickoff, because it's one part, all of you know that it's one part to have a small pouch cell in the small scale, or if you try to, let's say, bring it to a cell factory or material factory in a huge number. So this is a third point I really would like to emphasize: the maturity for scale up. And there we see in this current situation, 2022, a little bit of an advantage for the sulfidic electrolytes. So then there was even mentioned a lot of the benefits. So we see the 2 or 3 points, the intrinsic safety, rather going to a level of LFP right now, which is distinctive. And of course, the main driver for the technology is an increased energy, only to be reached in our eyes with a lithium or lithium free anode, to come beyond what is currently achieved by lithium ion technologies. And let's say it has to be competitive, as I mentioned before. That I would stick from our point of view as the 3 major characteristics. On the other hand, also mentioned, there are a lot of challenges. On cell level, even achieving this higher amount of safety is a big issue. I will dig in deeper later. Even the energy density with combining the lithium anode in this all solid and especially the interfaces working regarding the internal resistance are the main topics on cell level I would like to point out. And perhaps new in this, let's say, row of speeches is here more about the pack issues we are currently working on, and it's really would say hard work to find a solution for having this length variation of the cells, discharging by about 10%. We see in a lot of concepts. And even the, let's say, compared to lithium ion technology, order of magnitude higher pressure requirements to have the cells working in a good way, could be even more. And this is somehow a combination, either the one or the other doesn't matter, but the combination of both is really leading to a lot of technical effort to achieve a proper operation of the cells. Last point, also mentioned, there are different operation or ideal operation temperatures for the different cell concepts. And even talking about 45 or 50 degrees is really compromising the achieved energy density if you assume you have to heat up or keep isolating somehow the pack for a typical vehicle operation. That might be different in buses and continuous operated devices, but I think for vehicles that also has to be taken seriously into account for comparing the different technologies. So as I described, we are just doing the step coming from the technology to the consequences to be seen on a pack level and trying or working on a maturity check for the next 2 or 3 years, as we announced earlier. So one step deeper, perhaps, just touching the portfolio of we are currently seeing for the different technologies. So we use it a lot of internal discussions for, let's say, adjusting perhaps the different criteria or achievements for the different technologies. All of them put into a mixed, a big pot. All of these technologies put into a big pot and communicated by solid state. So we see at the lower left part, we see the current reference, so the lithium-ion technology, even some future steps ahead to increase the energy density. And by that, we see two major directions. One on the upper side, it's getting the electrolyte in different steps more solid. And that is mainly the advantage is really on the safety side for that, it's clear. And we do not see a very high, let's say, energy advantage by following the route. It's more on how to integrate the cell in the pack from smaller portions or with less safety mechanisms on the pack level, coming to a higher pack integration level, but not really on a cell level. The other side on the right axis, we see the integration of higher dense energy by incorporating the lithium metal anodes, and that is leading to, in the first step, less safety, combining the fluid liquid electrolyte with a let's say, activity of a lithium metal, both in the cell. So we judge that to be very critical and have a close look, nevertheless, on these technologies emerging on that side by a lot of companies. And on the right upper side, just to have this target where we are achieving, we think both to really have an let's say overall advantage, we have to come to the right upper side, combining, let's say, both technology achievements to have really the step ahead we discuss about the next technology. So just coming perhaps to the last slide, having some specific items we see and we would like to share with the community to have future work on. Of course, the material interface is clearly one of the most limiting factors, and that is somehow the point I mentioned before. High pressure as a prerequisite, or even the elevated temperature, may lead on a pack level to substantial disadvantages. So on the other hand, the interface, which is working well with a low temperature or operational temperature and less pressure, cannot be, or is so advantaged because it cannot be compensated on a pack level in our eyes. Even on a manufacturing side, it always has to be thought if this, let's say, interface based on a very fine structure can be industrialized to come to a higher volume, incorporating also a higher lifetime. And for example, we see even with scaling up technologies by a factor of 10 or 50, that comes really to a problem, having that on big areas, some homogeneous surfaces at this interface state. Then even touching the interface, we see it regarding the power prerequisite as perhaps limiting if the interface is two-dimensional. And because of the different, let's say, transfer mechanisms for electrons and lithium to recombinate, compared with the lithium ion, we see that even all concepts having, let's say, a backlash for the power requirements. For the failure mechanisms, we see even that point that there are mechanisms which work well for quite a lot of cycles, and then have a sudden death, so a more, not less degradation, but a certain failure mechanism which appears suddenly. And the last point also mentioned is, for me, the very most important point is the safety. And even there, scaling up from, let's say, a partial ampere hour or 1 or 2 ampere hour cell to an higher, bigger cell, you sometimes only then see the real safety behavior, because not having always a conflict, let's say, with a test infrastructure on a cell level testing. So that is basically all I would like to share today. So we could use the rest of the time for having 1 or 2 questions.
Thank you so much, Jürgen, for the nice overview of the challenges that you have in the industrial environment, which is very important for everyone to know about. I do not have any questions in the Q&A. Just a quick message to all of you. If you have a question, please use the Q&A function. Maybe a question from my side is, to which extent do you already integrate elements of circular economy into the design of the cell and the choices of chemistry?
For the basic idea, I would say it's the first step to specify, of course, let's say, concept which works and which even reduces the compromises, which I did not dig in on the system level, to reduce the pressure amount and the operation temperature. This is, of course, the first step. But nevertheless, we see that combining the 2 technologies, the lithium ion state of the art, and having this technology ready in the 2030s to have clearly what you said before, the circularity implemented, that the available materials by recycling in 2030 can be incorporated in these cells. That is a must, let's say, like this.
So it is well taken care of in the industrial environment, right? Okay. Jürgen, if there are any other questions, we will take it towards the end of the morning session if there is time left. So if you still have questions for Jürgen, do not hesitate to put them in the Q&A, and I will reserve them for the rest of the morning. We will now move across the border to another OEM in France, that is Renault. And I'm happy to have Xavier Rodrema with us. So I hope that you all managed to get some decent beverage before we start this second part of the morning session. So we will now hear from the battery cell making part of the value chain. So we are going up the value chain, 1 step up. And we will have a presentation by Mr. Depré, Philippe Depré, who has a PhD in process engineering from the Institut National Polytechnique of Lorraine. And he has a long battery industry experience, over 20 years, first at Alcatel, then Saft. And he joined Saft, a new program on solid-state battery, a couple of years ago. And ever since 2020, he's now at ACC, that you may know all very well. That's the automotive cell company. And there he is a senior battery expert and academic relations manager. So, Philippe, I will give you the floor right now.
Okay, thank you for the introduction. So I share my screen. Just confirm it's okay for you.
Yes, we can see the slides.
Okay, perfect. So I will introduce SCC and what's going on regarding SCC and solid-state batteries. So to start with SCC at a glance, and then more details about what's going on at SCC about solid-state batteries. So now SCC is a 2 years old company. With key objectives. Our main objective is to be the European leader of automotive battery cells and modules, and it's to enabling cleaner, efficient mobility for all. So it is a very focused objective, which targets the main mobility segment on the main market for the batteries. So our shareholders, 1/3, 1/3, 1/3 are Saft, Total Group, Stellantis, and Mercedes. So we have announced 3 gigafactories, but also a R&D center, which is operational at Bruges, close to Bordeaux, in France. Yes.
I do not know, your slides are not moving on our side.
Okay. So I come back like that.
Yes. Maybe you can put them in presentation mode as well.
Yeah. I come back to presentation mode. It's okay. You can see my screen.
It doesn't switch to presentation mode, but this is okay. If you change the slides, this is okay for us.
So I do like that?
Yes. If
okay.
you don't forget to go to the next slide each time, yeah. Thank you.
So, okay, I do like that. Yes, so I come back just to mention you, so the R&D center in Bruges, close to Bordeaux, which is operational. Also a testing plant in Nersac, which is operational, so it is for scale 1 equipment testing. And then 3 gigafactories have been announced, one in Termoli in Italy, start of operation 2026, the second one in Kaiserslautern, Germany, SOP in 2025, and the Gigafactory 1 in Billy-Berclau-Douvrin, north of France, SOP in 2023, totally speaking, a capacity of 120 gigawatt-hour. So I show you the existing expertise center we are working in. It is a 1,000 square meter building, 1,300 square meters of test area. So you can see the different fixtures. So it is a key point for us for our development. For all the technologies and all the projects we are dealing with. Then I present you already in operation also. It is a Nersac pilot plant. It is an industrial excellence center, so you can see one equipment in the picture, and you can see also the whole building. So it is 24,000 square meters of buildings. You can see the dry room surface, and it is it has been developed for validation and optimization of processes, and also for production of small series. But the key objective of this pilot line is to assess and to optimize the process. I switched to the first gigafactory, Billy-Berclau-Douvrin, because now it's happened. Same thing. You can see the building under construction. So you have the building. So it is a 600 meters long building, 100 meter width, and you can see the height with the small people. You can see of the top right pictures. So this building will be in operation next year, 2023, with different blocks. A first block of 13.4 gigawatt hours in production next year, and then 3 blocks to reach 40 gigawatt hours by 2030. So I presented to you the different evolution of SCC and what happens at SCC. If we look at the roadmap, the total the ramp up, so you can see 2020 was the start of ACC with the R&D center. Then you can see the main point are the phase 2. You can see the build of Gigafactory 1 and also the start of German R&D Center in 2022, this year. Next year, you have the start of operation of the first Gigafactory. And then you have the ramp-up production capability using the three Gigafactories, reaching by 2030 120 gigawatt hour. So now I come to solid state. So why do we need solid state? First of all, it is a market. It is an innovation pool by automotive for a profitable market growth. So it is to start with, it comes from the market. Then you have a technology, also a technology need, because we know that current lithium-ion technologies are reaching their limits. We improve by incremental improvement, but nevertheless, we can see their limits. So we need disruptive technologies. It is the case with solid state. And so for SEC, it is strategic to be the European leader of automotive battery cells and modules. So principal benefits, I will not deep dive on that. You have already had presentation on solid state batteries, but to show you how it can be seen by a battery manufacturer. So we have a conventional lithium-ion battery we call Gen 3. So it is you have a porous anode, a separator, and a cathode. So it is a traditional battery. And with solid state, so you have a anode or anodeless, but mainly speaking, you have an anode, a lithium anode, a dense solid electrolyte, and a dense also cathode composite for the positive. It can be bipolar or not, and you can see a prototype on the pictures. So the principle is to replace the liquid electrolyte by a solid electrolyte, okay, and also to replace the graphite electrode by lithium or silicon or by anodeless solution or whatever. And the benefit which are expected is first to improve the safety. That means to be at hazard level, to be below UCAR 4, that means no flame. For the different safety tests. And also a key point is to increase the energy density, the volumetric and the gravimetric one, with expectation as has been shown up to 50%. How we work on that, we have collaboration. So a key collaboration in October 2022, SEC and Prologium are partners and signed a MOU to accelerate the development of solid-state EV battery. So you can see here the CEO of SEC, Yann Vincent, and also from Prologium, signing the MOU. So it is to join the force in a new strategic partnership. And both companies are leveraging their own expertise to jointly develop state-of-the-art EV solution and solid-state battery. The battery technology considered the most promising in terms of safety, energy density, hyper fast charge capability, recyclability, weight optimization, and so on, cost and lifetime. So it will allow SEC to strengthen its position as a European leader in automotive battery development and manufacturing. And for Prologium, it solidifies its position as a leader in solid-state battery technology. So we are developing such key collaboration as an enabler to provide solid-state batteries in automotive. We have also collaboration, of course, to tackle this point. We have collaboration within the Battery Alliance. It's built European industry champion, and it is based on material, process equipment, automation, and digitalization. Okay, you can see on the picture the partners of the Battery Alliance. I can name Saft, Solvay, Umicore, Applied Material, and Mans for Müller and Siemens. Okay, as partners of the Alliance. Another way of collaboration is also the support from European national authorities, which push also to develop projects. So here you have the picture of the different key players. I want to mention EMIRI, funded EMIRI, which is supported by the European Commission, which is a main levers of this development. As a collaboration, we have also a joint program with SAFT, ICC and SAFT. On here, I can show you some results for Gen 4 polymer with lithium metal 1 ampere hours cells, and also on sulfite technologies. To conclude, solid-state batteries are a technology, but for us, they will become a project. They are in our roadmap, in our technology roadmap. The roadmap includes two technologies, Gen 3 with nickel NMC 811 graphite with already more than 600 Wh per liters. You can have the use on different NMC chemistry, 7370, for example, at lower energy density, but which can be more optimized for cost perspective. Then on the roadmap, you have also Gen 3 Plus, which include graphite and a blend of graphite and SOX and the negative electrodes to increase the energy density. And then you switch to Gen 4 and Gen 4 Plus chemistries with a target to increase the energy density. So you can have a look for the Gen Plus in 2028. So instead with a nickel oxide, high white solid electrolyte on the lithium on the negative with more than 1000 Wh per liter. In parallel of that, of course, here we have spoken about product. In the roadmap, we have also, of course, process evolution, and you can see here not to have recycled NMP and then to switch to dry process to no NMP inside our manufacturing sites. So here are the different activities of ACC related to solid state, and I hope that you take information following this talk. Thank you.
Thank you, Philippe, for the overview. I'm trying to consolidate a few points into one question for you. Basically, the question is, when you are programming the ramp up of ACC capacity going forward, how do you take into account a couple of elements? The first one is the pricing evolution of raw materials and the availability. And the other question that is linked to that capacity ramp up is, how do you take into account the changing battery cell design and the need maybe to change some equipment or adapt equipment to the new technology?
Yes, you're right. Of course, when you have a ramp up, so you make several blocks, but it's not me too, I would say, process. That means for each block you can make evolution for the technology, for the active material. So of course it is based, all this ramp up as based by different phases. On these phases you can have some evolution. Of course we have we consider all the points you have mentioned. They are important.
Thank you, Philippe. So if there are any other questions, I will then keep them for the end of the morning session. And I will now move to Gilles Normand from Prologium. Quickly about Gilles, trying to boil it down in a couple of points. Gilles has been active in the field of automotive industry for more than 30 years by joining first Renault, where he has held some leadership position as vice president, In 2017, he was the SVP for the Global Electric Vehicle Business Unit. And in 2022, he has joined Prologium, that we have already heard about. And he is there, the Executive Vice President for International Development. So Gilles, you have the floor.
Thank you very much. I hope you can see well my presentation.
We see everything.
Hello, everybody. So we are first a company from Taiwan with 16 years of history of experience, and I would say with the intention to expand internationally by deeply rooting ourselves now in Europe for R&D, for material procurement, and for hopefully a gigafactory that we do intend to build in the near future. In terms of short company presentation, in these 16 years, we have been able to register more than 600 patents. We have more or less 600 employees in the ground here in Taiwan. Almost half of them are from R&D. We have already raised a little bit more than $600 million of private equity. And this is important because it does give us the capability to start developing some concrete element. We've been able to sell small cells to a global customer, especially consumer electronic ones, from 2013. And we are now busy delivering cells to the automotive industry, to OEMs to qualify our technology as we speak. We just got two key shareholders in the automotive sector. So Mercedes-Benz has taken a share in our company a little bit more than 6 months ago. And VinFast, Vietnamese full electric new entrant, has taken a share about 3 months ago. And as it has been said by Philippe, we have built a strategic partnership with several companies, including ACC. So if we speak about our product line, it all starts with, if you can see, this is our inlay. This is where you got everything is quite thin. You got everything in it. It's our product line is based on especially 3 COS awards, 2 Edison awards. And now we are busy developing it, as you can see on the left column, for automotive application. Up from what we did on the right part was especially for consumer electronics. Our technology is very thin. It's very safe. So as it is very thin, it does qualify for credit card, connected credit card, connected helmets, connected watches. Our technology is extremely safe. So it means that you can cut our cells, you can make the nail test, nothing will happen. And then we do qualify for explosion-proof material. And now we are busy developing for flying object, aerospace, ESS, and obviously vehicle application. So we do rely on 4 core technology. The first one is oxide electrolyte. So it's a solid one. It's not all solid-state batteries. At this point of time, we are speaking about solid-state batteries because we still have a 4% mass of gel within our electrolyte. But we still have, and this is the most important element, the safety. Once again, you can make the nail test and nothing will happen. But it's very important from a manufacturing process because we can manufacture our inlay with a reasonable pressure. We go up to 1.4 atmosphere, so which is quite efficient from a manufacturing standpoint. And we do have a ceramic separator, which is important once again, because as you know, ceramic is quite solid and you don't have any intrusion in case of in case your cell once again is affected. We do have as well ASM. ASM is active safety mechanism. So we do prevent organically thermal runaway at the level of our chemistry. This is very important because we don't need to have protective measures at pack level. And to improve conductivity, we have developed bipolar plus technology, which fundamentally high conductivity with less material. So this is obviously a little bit simplistic view of what our technology brings. Obviously, if we are under NDA, we can share the two third-party tests we have done comparing other technology, and we'll see that our technology can go through nail tests with absolutely no issue. And this is what is important because it's a significant improvement in terms of safety. We did a feature in last Mondial of Paris, early October 17th, as a world premiere. Our new cell, this was, we replaced completely the anode. The anode is 100% silicon oxide. It enables us to double, more or less at pack level, the volumetric density. Fundamentally, if you had a car like a Tesla Model 3, 60 kilowatt-hour pack, you would move from 560 kilometers to almost 1,000 kilometers. We can charge it at 5C. So for the same Tesla Model 3 60 kilowatt-hour pack, instead of charging it in 30 minutes, you would charge it in 12 minutes. So it means that from a customer perspective, if you got safety plus high driving range plus fast charging capability, hyper fast charging capability, then it paves the way for a dramatic improvement in the electric vehicle adoption, no longer pushed by the regulation, but pulled by customer adhesion to the vehicles. On top of that, we do have a very high level of recyclability, and we do have approximately 30% at pack level of weight reduction per kilowatt hour. So this is available next year to be tested at the level of car makers. So our intention, and here it's discussion versus previous presentation, but we are convinced that there is a room for a silicon-centric road, and this can happen quite in a, let's say, in a decent horizon. As you can see here, we can put our proposal is we've started developed the what we call generation 3.5, and here I'm speaking about a gravimetric density. As you can see, our generation is from 240 to 330 watt per kilo. It is based on NMC 811 plus silicon oxide 100%. Then we will develop further with NCM 955 and lithium-rich plus silicon base anode. Then we will go for a lithium metal anode. So as you can see, we have a very, very long roadmap in order to develop. More importantly, because we have a good visibility on the chemistry, and we are busy developing the associated manufacturing process, and we will test it only next year in our new plant in Taiwan, but this plant is going to be limited in scale up to 3 gigawatt-hour. The massive evolution in terms of production capacity will happen with a gigafactory we want to open, hopefully, in Europe. But very important, we want as well to develop an overall and comprehensive view on the value chain. So as you know, we are already busy working with OEMs. We discuss with cell makers, obviously, with ACC, with a strategic cooperation. And we would like, obviously, to have a very advanced discussion with material supplier because we want to localize everything in Europe. So Umicore, of course, Solvay, and BASF. So I will conclude here my presentation and hopefully have maybe some questions from the audience.
Thank you so much, Gilles, for the overview. I have a question on the cost. I don't know to which extent this is an answer that is possible to answer, but how do they compare cost-wise 100% silicon oxide versus the graphite electrode? What is the differential that you have to deal with?
So if we were to speak with a 30 gigawatt-hour factory in place, and this is the intention to go for 48 gigawatt-hour factory in a reasonable time frame by 2030, then our cost structure would be potentially lower than the current technology cost structure because our process is simpler. It does emit less CO2, it uses less energy, and it does use less material. So that's a very important point. Second very important point, strategically wise, about more than 70% of the graphite is coming from mainland China, where we think that there is a good route to have silicon and silicon oxide coming from Europe. So this is as well something which is quite important to reduce CO2 and to reduce cost.
Mm-hmm. And on the recyclability front, have you already done some testing as to which extent it's easy to recycle these batteries back to the raw materials?
Yeah, it's a very good point. And we did it for this generation, definitely having the recycling in mind. We have a very high level of recyclability. We consider that more than 90% of our material is recyclable, so which is a significant step up versus the current generation. So on this front as well, I guess it's a quite healthy improvement.
Thank you, Gilles. So very nice developments going ahead, and good luck with the European integration, I would say, in the months to come. I would now move to the next speaker from Solvay. We're happy to have Mrs. Bouissette, Valérie Bouissette, with us. So Valérie has been doing a PhD in material science, and after that she has been joining Solvay. She's involved in solid-state batteries since about 2015, and at Solvay she's the head of the solid-state battery activity. So Valérie, we are eager to listen to the materials provider point of view right now.
Thank you, Fabrice. Yes, so now we are moving to material supplier side. So I will present some highlights that we have on the solid electrolytes for solid states, knowing that Solvay is active both in polymeric binders and electrolyte ingredients for the battery field. So as was already said, that I will go fast on that. So current generation of lithium-ion are reaching their optimum, and breakthrough are expected to reach.
Valérie?
Yes?
The slides are not changing on our side, so yeah.
Okay.
Thank you.
Same issue. Is it okay like this?
It's not in presentation mode, but on my side it's okay. We just need to make sure the slides are changing. Perfect.
Yeah, yeah. So breakthrough are expected. First of all, probably in energy density, as was mentioned, but not only so, without compromising fast charging, better safety, cost, and also the fact that we need to move all to more sustainable designs. And in that field, solid-state batteries are expected to be a major contributor to this breakthrough innovation. I use a drawing inspired from Fraunhofer to define the types of possible systems. There is a complexity here, but the main point is that the electrolyte should go to non-liquid and non-flammable in order to enable mainly the use of new anodes and to have a better or more compact designs at the cell and the pack level. So among the different options, possible options, Solvay have chosen to focus mainly on sulfide electrolytes that has been seen as very promising for EV application due to the very high lithium bulk conductivity and good processability of the electrolyte in composite designs, and the possibility to enable high breakthrough in energy density. This is, I would say, confirmed by a recent announcement by cell maker in OEMs to rank this technology with a high potential. If we move further in this, we see this with 3 levers for success. The first one is we need to deliver high performance and scalable chemistries, so high performance electrolytes for sure with high lithium conductivity and processability. But we need also as well innovation in binder solution that needs to be adapted to solid-state battery constraints, and to have a good integration in the composite systems or intensified layer depending on the technology we choose. The second pillar for success is a large scale and local production. So the difficulty, as was mentioned before, is to go to a higher level of proof of concept, is to be able to have cell design at above 20 ampere hour for especially for safety test validation. And for this, we need to be able to provide sulfide at significant size and significant reliability, which means translated into a chemistry design with a pilot assets at ton level. And we need also to anticipate the industrial implementation plan to be synchronized with OEM demands. And of course, as was also said, there is a clear need to have to invent sustainable processes from the start with ab initio eco-design. And last pillar for success is collaboration along the value chain and financial support from the authorities to secure these breakthrough projects. So as I said, we have defined our choice mainly on sulfide. This is a challenging journey to develop high-performance sulfides, and we see it in a 4 direction. The first one is solid-state chemistry. Of course, we need to have a good sulfide, I would say, composition to ensure lithium conductivity and chemical stability, but it is far from being enough. The second issue is management of holistic interfaces. First, at the casting and at the manufacturing of the electrodes. And secondly, in use with managing interfaces in terms of chemistry, electrochemistry, and mechanical compatibility with other components of the cell, starting with the cathode active material and anode side. The third point is how to have a good imagination of the cell design. Do we need new cell design, new assembly designs, and do we need to move from now to solvent-free processes? This is still open question. But the way we address it at Solvay is also the first pillar, which is very important, is to go beyond the glove box from the start. Many of publication and patents are made on, I would say, designs of electrolyte that are made in glove box, but this is a main drawback in terms of fast and realistic scalability of the processes. So we had made the choice from the start to use only scalable processes, large-scale enough tools, and to work in dry room environment and not in glove box, to be sure that these processes are scalable. We have implementation of KiloLab tools which is running since 2020 in Paris. And we have announced that we have started 2 months ago a state-of-the-art pilot unit in La Rochelle, France. So this pilot is based on the existing plant of Solvay, which is managing all the environmental part and which is ready to implement at larger scale. It's a semi-industrial pilot which is able to manufacture several tens of tons of sulfide at maturity. And this was made possible by the support of the IPCI and the Nouvelle-Aquitaine region. So finally, Solvay is committed to supply at industrial scale, quality and cost, the new electrolytes, inorganic electrolytes, so state-of-the-art inorganic sulfidic and oxidic powders that I didn't mention yet. We also work on adapted binder solutions for this application. We have a unique pilot asset in Europe, which is ready now and which is starting, and we have planned our industrial development plans in Europe as well. And finally, we have a strong collaboration network, and one of the examples was already mentioned by ACC's Battery Alliance with the actor mentioned, to be sure that this technology can be fast on the market in Europe. I thank you for your attention.
Thank you, Valérie, for this materials side of the discussion today. There is one question on the Q&A, which is about the toxicity of the sulfide. How are you going to address that point when considering the disposal of the batteries?
So there are 2 points. So one, you can play on the composition of the sulfide to tune the safety aspect. And second point, we are also working on the recyclability to be sure that these types of electrolyte can go in the flow of existing or adapting with a smaller adaptation in the flow and recycling, classical recycling flow. So this is
and when we talk about the large-scale production, we are talking about wet synthesis of these sulfides.
I will not comment on the synthesis route.
Okay, I understand. Just checking the Q&A. Yes, there is a question on the last slides. They also state activities in the oxidic powders. Is it possible to elaborate on that?
Yes, so the oxidic powders is it's at lower scale today. It's I would say it's a good fit with our existing technology, because we have existing background in rare earths and zirconia field, so it's very adjacent technologies to previous technology that we have, but we have I would say less clarity on the market adoption on the oxide compared to the sulfides.
Thank you, Valérie. I think it's clear for all now. I will then move to the next presentation, which is by Umicore, by Godwill Bancol, who has a master in engineering from Telecom Paris and a few other degrees in finance and MBA. He started, many people started at Renault. He started about 13 years ago at the alliance between Renault, Nissan, and Mitsubishi. And after that, he was active in a consulting company that he created, and he has recently joined Umicore, where he's active with the solid battery ecosystem as part of the new business incubation center that we have in the company. So, Godwill, you have the floor. Well, if Godwill is here, because I do not see Godwill joining. What I propose to do in order to solve the problem with Godwill is that maybe we give the floor to you, Andreas, from Scott. Is it okay for you, Andreas?
Yeah, that's okay.
Okay, so let me briefly introduce you. You are a senior project manager, a new venture at the Corporate Research Center of SCHOTT, that many of you may know, which is a company based a company with a long experience in products in specialty glass. Sorry, you are in charge of finding new product opportunities, and since 2010, you are responsible to develop materials for the advanced lithium batteries. And today, you will talk about solid electrolyte materials used at SCHOTT. And I think in the afternoon, there's also a project in which you are part, which is Safe Lithium Move, that you will tell us more about. So. Andreas, I give you the floor.
Yeah, thank you very much for the kind introduction. It's really a very good session that we have here, and we are turning now from the sulfides to the oxides. So just the basic principles, of course, this is known. The solid electrolytes are replacing the liquid electrolytes for higher energy density, higher safety, fast charging, and lower cost. And at SCHOTT, we take care for the oxidic electrolytes. And the most promising materials glass are the LLZO and the LATP. These are the two material classes we are working on. So who is SCHOTT? As already mentioned, we are a specialty material company, in specialty glasses. And coming from the material, we have a broad product spectra established, and one I want to emphasize, and this is in home appliance, the glass ceramics that we are producing there. The glass ceramics will play an important role in my presentation, because this is the approach we are taking also for the solid electrolytes. One important point is sustainability. So at SCHOTT, we are committed for climate neutrality in 2030. And the second point is the melting route that we are taking is really one of the best routes for recycling. You know this from bottle industry. You put just the bottle in front of the tank and remelt it. This is really the best way for recycling, and this is also possible with the materials that we are preparing. So what has SCHOTT to do with batteries? It's not so straightforward, but you can see there are a lot of things that we are doing, from thermal fuses, battery caps. We have HM scavenging powders for lithium-ion batteries, and also the lithium-ion conducting materials. And here we are really going for the industrialization of the high-performance solid electrolytes. I think this is an important point beyond all the R&D that is done. Really going to scale, as already mentioned in the talk before, is one of the most important things that we have to do at the end. And for the oxides, we see this as a big advantage, the scalability, especially at SCHOTT, because we are using the melting process for the upscaling. So this is a well-established processes, and we believe via the glass ceramic approach, we can make these kind of materials via the melting process. The second advantage is there in the glass ceramic route is we can take care for two main challenges there. And one is, of course, the high ion conductivity in the ceramic, but also to take care of the interfaces, designing of the interfaces by introducing an amorphous phase into this kind of systems. So if we look at the players all around, you can see this is widely spread. Of course, as a material supplier, we have to take care of the worldwide activities here and see what is going on there. And in Europe, what we see is that we started in Europe with some specialty battery producers like Saft, which are now turning also into automotive space. So and also what we see is that the industry has realized that also solid state batteries are of increasing importance. So also here in Europe, the activities are really increasing, not only by the established players, but also by some new startups. So cells are announced already for the commercialization, but what we see is that this might be only the first generation. So there's, especially in China, what we see is the penetration of semi-solid state batteries, which still contain liquid electrolyte with some advantages, but also staying with some of the disadvantages. So there is still a lot of R&D ongoing and necessary to make really attractive our solid state batteries. So what are the challenges in the solid electrolyte? I think this is an important slide here. We have already seen that there are three prominent material classes: the oxides, the polymer, and the sulfides. They all have their pro and cons. So what does a solid electrolyte has to deliver? First is it's the compatibility of the materials and the processes, and this is especially looking at the interfaces, but also making a cell, so integrating it into a cell. Ion conductivity, of course, has to be high, especially at the cathode. One of the most important thing is really if you want to go to high energy density, you need the lithium metal anode or an anode-less design, and there the dendrite stability plays a very important role. And at the end, as already mentioned, cost-effective scalability of the solid electrolytes is also a must at the end. So what we see today is none of the prominent electrolytes is really doing the job. So they have all their pros and cons. That means there is no clear favorite concept. And as we already heard also from BMW in the morning, the race is still open. But I would today, what turns out, it's not a race of the competition, but it's maybe also a race for the best combinations, because what we see is a quite clear trend for hybrid solutions. So you can combine the hybrids in polymer and in oxides. You can also hybrid cell concepts that you have an oxidic separator, but on the cathode you take a liquid or sulfidic cathode. The number of concepts is increasing now, and this is of specialty importance if you're developing materials, because the materials must fit into the cell concept, and that's why you need flexibility in the material design. So what we do at SCHOTT is we take care of these cell concepts which are out there in the world, and we adapt our materials to special cell concepts like sintered cells or for hybrid cells. So all this, we have adapted solutions, and the R&D is still ongoing. As I mentioned, the process that we take is the melting process. This is a special unique for the LZO, where nobody else is able to make this via the melting process. So, and this is just an overview what we have. As I mentioned, we see LATP and LZO not as a material, but as a material class. So we are tuning this, and you can see this is, of course, the core is a crystal structure. But one of the problems is always the interface. At the interface, you don't need a crystal structure. Sometimes it's even disturbing a crystal structure. And there we introduce an amorphous phase, which can tune the ion conductivity, which can tune the sintering temperature. And you can see for LATP, for instance, we could decrease the sintering temperature from 1000 to 700 degrees C. In the LZO, it was from 1200 below 900 degrees C. So this is something which is possible if we take this glass ceramic approach, and the R&D is still ongoing, especially also to combine it with polymers and also LZO variations really designed to enable the lithium metal anodes. So we are doing this in corporations. As you can see here, funded projects play an important role. So here are some examples that were for the corporations that we had or that we still have in Germany, as well as also in Europe. The Safely Move project, you will hear much more in the afternoon session. And with this, I want to thank you. I think we are already on the way where we go for industrialization on one side. On the other hand side, for the advanced next or further generations of also the solid-state battery, which are more attractive, there are still a lot of challenges which have to be overcome. So thank you very much, and I'm open for questions.
Thank you, Andreas. It was nice to have the vision from another kind of material provider. So with Umicore, Solvay, and SCHOTT, we tried to give a broad overview of all the materials challenges. I have no questions in the Q&A, but maybe on my side, can you comment a bit more on the timeline for the different generations of materials that you provide or that you develop?
Well, we already have, I think, in total 7 versions of LATP, LZO. So these are already available, and you can test them in your systems, and they are also now spread all over the world for testing and for integrating them already in the batteries. But we see further development need and also progress which have to be made. And this will be in a time of 1 and 2 years, where we see that we think that we will have significant progress also in other fields.
Okay, thank you, Andreas. And indeed, in the afternoon, we will be talking about the European projects, and one of them is Safe Lithium Move, of which SCHOTT is a partner. So thanks a lot, and we managed.
Thank you very much.
We managed to have Godwill now. So Godwill, you have the honor to close the round of presentations of the industry. So you have the floor.
Thank you. Thank you very much. Can you hear me?
Yes, and we can see the slides. You can put them in presentation mode. Yeah.
Is it okay now in presentation mode?
We see one slide and the next slide, so it's okay. For me, it's okay.
Okay, so let's go through the presentation. First, I propose just to structure the presentation in two parts. The first part is just industry level, and then in the second part, I will focus on Umicore solid-state battery approach. So on the industry level, I think there are already so much knowledge that you have on it. So I will not go too much in detail, but it's always good to remind what is going on globally. So solid-state battery, what is it about? Is about bringing increased safety and energy density, and then you have other additional value. And here, what we are showing is really how solid-state batteries compare to existing technology like the lithium battery, lithium-ion technology. So what we expect from solid-state battery here, for instance, is a higher volumetric and gravimetric energy density, and you are all aware of it. And concretely, what does it mean in terms of value to car makers? It means that first we are, of course, improving the performance. It's also mean that we are saving space and weight in the car, and this can also impact then the architecture and the design of the car, giving more flexibility to the car makers. And it might also mean that actually we are lowering costs. It's not proven yet, by removing some steps and resolving some issue like the cooling, which will not be required in solid-state battery. What we can also say is that actually between the lithium battery existing technology now and I will say the end of the game, which is the all solid-state battery, there is an intermediate step which we call semi-solid, which is actually pushed by China. And we can already see this technology coming to the market around 24, 25, 26. So we have here a kind of spectrum of different technology going on. And then we have multiple options depending on the cathode, the electrolyte, and the anode. So on lithium-ion battery, you know that the anode, for instance, is a graphite and silicon-based anode, whereas when we move to all solid-state battery, we will consider anode-free technology and also lithium metal anodes. And you can also see below here what is the range of performance expected for all those three different categories of technology. Solid-state battery, as we remove the liquid electrolyte and we replace it by a solid electrolyte, it actually has a significant work also on the cathode part. And here we are sharing with you what it's really mean on the cathode part to extract maximum value in solid-state battery. And it requires us to work on the core of the technology, but also to work on the interface of the technology between the cathode and the electrolytes. And of course, when we put these materials, depending on the size of the cells, the level of pressure, of temperature, this has different impacts. And then you have a closed loop between the design of the cells and then the performance of the materials in that cells. And this is why actually in solid-state battery, you see really the strong link between cathode and electrolyte and later anode, which requires really strong collaboration between the different partners. So globally, this is a quick overview of the industry. I did not spend too much time there because I think you are quite well aware of it. Now in Umicore, what is our approach on solid-state battery? On the right, you see really what are driving Umicore. We present Umicore's RISE strategy for 2030. Our CEO presented this quite recently. It was in June. And then we have actually really three driving force: the mobility transformation, the growing need for advanced materials, and the circularity. And our ambition is really to drive solid-state battery innovation pushed by those three forces. And in order to do that, what we are doing is that we are leveraging the different expertise that we have in the company. We have expertise in rechargeable battery materials, We have expertise in electro-optical materials. We have expertise in battery recycling solutions. So we are putting all this expertise together really to bring the solid-state battery innovation to the market. And in terms of ecosystem, we can say that we are working with 3 different categories of players. We are working with technology enablers, and most of the time they are very advanced startups which are licensing this technology or want to enter the cell making segment. Then we are working with cell battery makers, and we are also working with car makers. So it's important for us really to work with all the different players to bring this technology, because those different players play different roles and address really to, I would say, different aspects of the adoption of that technology. How does the solid-state battery solution portfolio looks for Umicore? As we really have this system approach, and for us, solid-state battery is really about optimizing the full system. We come up with a quite broad product range, which we can really customize depending on the customer we are, or depending on the partner we are working with. So you can see that on the cathode, we provide cathode from medium nickel to high nickel and to HLM and low cobalt. We are addressing the different type of electrolytes. And then we, using cathode and electrolyte, we are working on the concept of what we call a catholyte, which is actually already to pre-match and to pre-integrate the cathode and the electrolytes already to optimize the performance of both. And then also we work on glass, because this is the separator layer, and is quite is an interface to the electrolytes. Also, what we have is that we have application facilities to really help us to test the performance of our materials under different cells conditions. And these are different size of cells. So we work up to 5 ampere-hour cells and even above to really test how our materials perform and improve then the performance of the materials. In terms of a roadmap, I don't share with you a let's say specific roadmap. I prefer to show you the different wave, because at the end, as the material solution providers, our roadmap is quite influenced by our customers. So depending on the SOP of our customer, we have a retro planning, and we really align with them on the target and have some flexibility as the technology is not mature yet. So our roadmap quite depend on the customer. But what we can say globally is that we see 2 waves. One wave, which is the semi-poly wave, where we are already having SOP around 25, 26. And in that group, you have different players with different timeline. The early ones are already requiring a medium to large volume in 24, 25, 26, whereas the others who are coming a little bit later in that wave. Then we have the second wave, which is then the wave of the all-solid-state battery, and that one is targeting SOP around 2030. The early players are coming around 29 and are already requiring significant volume, whereas the others will come a little bit after 2030, so between 2030 and 2035. And so globally, if I can comment here, we have a very large, I would say, network of partners with whom we are co-developing the technology, making sure that we can really address the market needs for all the different waves and all the different technology options that we have. I will conclude here just saying first that we are really moving fast on the solid-state battery. We are no more at the, I would say, on the R&D stage. We are already at the pilot stage, and even so when I say pilot stage, we are some time already scaling up the pilot stage and already having some mass production discussions. So we are really fast on that and quite well advanced. What we can also share is that we see that solid-state battery require high investments, because now it's not only about developing the product, but is due to the fact that we have all these parameters of how the materials perform under cell conditions. We have a lot of work to do to test really those materials in applications. And that means that we have to invest in application up to 5 ampere, 20 ampere, 50 ampere hours, and those are big investments to really optimize the performance of our materials. It's also important to share, to be aware that the lithium battery technology is also evolving. Then we are not competing against the lithium battery technology as it is now, but with the future version of that technology. And we are paying attention to that to make sure that we are delivering value on ahead or superior to the future lithium battery. Nobody knows yet the future, but it's a point of attention. The other thing is also that we see clearly that there are multiple technology options running in parallel. We have the multiple options on the anode side, multiple options on the electrolyte side. We have also multiple options on the cathode side, and most of the time it's not only about optimizing locally, for instance, the cathode or having higher capacity, but it's really about how the full work together. So we keep really the options open to see, and we think that in the coming years, we'll have a better visibility on the segmentation of the technology product per customer. I already should talk about the systemic optimization, which requires strong co-development partnership. And here is very important in our strategy. We are not really engaged in a supplier-customer relationship, because this is really a co-development approach, which is mandatory. So we look for players who want really to co-develop the technology with us and have a very deeper conversation about bringing the technology to the market. Recyclability and sustainability are critical. It's too early to really give practical solutions. We have the recycling business unit in the organization, and we are working with them to leverage all the process that they are putting in place for the lithium battery to see also how we can adapt it and use it also for solid-state battery. And then the last point is for sure, we see really a regionalization where we see North America, we see Asia, and it's clear that for Europe, if we want to drive this technology, we will need some significant EU support to really scale up the technology. That will be all from my side. Happy to take questions. I'm not too much knowledgeable about technology, so if there is a very deep question, I can take them and come later to answer by email, but I can answer globally about the strategy and what is going on in the ecosystem and how we are running actually the innovation for Umicore. Thanks.
Okay. Thank you so much, Goodwill. I think it was good to stress at the end the systemic element indeed, and the fact that it's more about partnerships than traditional relations. So it's an important point that you made. I'm checking the Q&A. There's a question whether you could elaborate on what we are doing at Umicore when it comes to combinations with glass.
What we are doing with Umicore when it comes to combination in glass is actually, I would say, at early stage. We are running 2 projects actually with some customers. I cannot name them. And one of them, for instance, is a car maker, clearly. And they come really saying, okay, that they want to see how our glass can help them with for the separator. And so what we set up, we set a kind of a joint development agreement to explore then together, and we are still at the POC, so it's too early to give results. And I think that in coming months, years, we can have further clarity on that.
Okay, thank you. Another question is about oxides. Are we excluding them in the developments when it comes to combination with the cathode materials?
No, we are not. We really adapt our approach to the customer that we have, and actually we have some customer who are using the oxide technology, and then we are developing with them. But of course, our approach is first to focus on the performance which is target, and then we can see what is the technology which allow to reach that target. And then comes the question about how we can scale up and to see if we have significant volume on that. So what we see currently in the market is that the oxide is still have kind of the low volume expectation. So we are not ignoring the oxide technology, but in the long run, it does not seem to be the one who is winning. It's more in the long run we are more seeing the sulfide electrolytes taking a big share of the market, with of course the semi-poly a little bit earlier.
Thank you, Godwill. I think we will close it for your part now, and maybe I can, so you can stop sharing. And before giving the floor to Sigmund Kielland and Daniel Glösner, maybe there's one question that I think it's interesting to ask the panelists if they can give us quickly their feeling about it. Is how do you see the use of LFP or LMFP in solid-state batteries? And after that, we will give the floor to the key takeaways. So if some of the panelists want to react on LFP, LMFP, sorry, that would be the right moment to give us your view on it.
Yeah, maybe I can quickly comment on that. So I think for the polymer SSB, that is very promising at the moment because it's compatible. But when we look at more at automotive applications in the future, to reach higher energy densities, of course, the other materials are more promising. So I don't think that we will see oxide-based or sulfide-based SSB with LFP, because I personally think that especially initially, we will see them anyways in premium products first. And in the premium product, there is no such big driver to use actually than LFP or LMFP. That's my my thoughts on that.
Thanks, Thomas. On the panel, anyone wants to support or have a different opinion than this one? Or everyone agrees? Rodrigo.
Yeah, no, I can just say, like, I mean, it's more or less along the same lines, but just to emphasize that, I mean, there are a couple of key factors why LFP has been increasing its market share, right? One is cost, one is the lower supply risk, and the long life cycle, for example. And if you think about it, I mean, would that make sense to combine that with solid state? I think if you combine LFP with solid state, it would become probably more expensive, right? You would potentially reduce the attractivity in terms of supply risk, let's say, with additional materials that are going to be more, let's call it, complicated. So, I mean, what do you gain from that? Let me put it that way. And I think that's kind of the equation that I think somebody that is proposing the combination would have to think about. The reason why companies like, for example, Blue Solutions have been using LFP or with their polymer electrolyte is precisely because of the chemical compatibility. But if they could, and if the polymers and or other electrolytes would be compatible or better compatible with higher voltage cathodes, they would actually gladly do so. So
maybe from our side, really, we don't even believe in LFP in SSB. So I think I share the previous comments. And then maybe one challenging thinking here is that even on the cost, not sure that the cost of LFP is really beneficial. It depends on the applications. And when we run some study and we consider the TCO, it's the conclusion was that even on the TCO, LFP is not always a really winning technology. So I think the cost advantage can be challenged, and we don't see LFP in SSP.
Okay, thank you, Godwill. So 3 important messages, quite aligned, I would say, on this approach. Maybe now I can give the floor to the key takeaways. First, from Sigmund Killand from EIFE in Norway, so more from the research organization point of view. And after Sigmund, Daniel will finish with the takeaways more from the industrial point of view. So Sigmund, you have the floor.
Yes, thank you. So first of all, I'd like to thank all the speakers from this morning. It's very interesting to hear both the market overviews in the beginning and also from the industrial point of views after. And then, of course, coming from the research side, it's good to see that's lot of research still required, lots of problems and challenges to solve. So looking forward to the collaboration in the years to come as well to solve these challenges together. And then some key takeaways. I mean, it's a lot of factors we could go into, but I would specifically mention them both the safety and the sustainability side. And the safety, which was mentioned before and was mentioned especially by BMW in the beginning, that the safety or the so-called intrinsically more safe solid state batteries, they would also need to be validated in their final applications to see the more realistic boundary conditions, because even though you remove the flammable electrolyte and so on, you still have challenges you need to solve. So just like to comment on that, and that we need to continue working on the safety side. It's not solving itself. So but it's good to see that Prologium, for example, have already a solution on this on the evolution. And then on the sustainability side, and then starting from this morning when ADL commented on the different, or how the different drivers are changing, that it's now not only the energy density going forward, that it's also sustainability and safety, of course, as mentioned, that also need to be solved to be competitive. So it's good to see that that this is also changing now, because we want a more sustainable solution to cut greenhouse gases and so on. But then to understand these different mechanisms, because I think many of us in the room here come from the natural sciences and material science and chemistry side. We of course understand that. So when it's changing also towards the sustainability side, and also when policies are supporting, I think these partnerships such as EMIRI and BEPA are very crucial. And also when facilitating this meetup between industry and research, it's crucial. So I just would like to take the opportunity to also thank the organizers for today, both EMIRI and BEPA. And then hopefully we can work together in the years to come also to solve these challenges together and see the different perspectives.
Thank you, Sigmund. So now, Daniel, the industrial part is always, of course, welcome to see how different or similar they are from the ones of Sigmund.
Okay. But first, also thanks to all the presenters and for the very interesting presentation and discussions. I put some bullet points. I think, as we know all, there are 3 main routes to ASSB, polymer, oxide, and sulfide. But for the time being, it seems, globally at least for the EV market, that the sulfidic solutions are probably at the forefront, even if all the other solutions, I think, will find applications perhaps in EV or in other applications. No doubt about that. The second point is the timeline for, let's say, the commercial, the really commercial application of ASSB is still very difficult to predict. But it seems that it will be probably in premium segments like drones, aerospace, or military, or what. And the shift to EV, well, I still don't have a crystal ball, but we have to take that into account. I also think that an interesting point is the emergence of semi-solid technology, which could be a bridge between the today liquid technology and the full ASSB. I think there are probably a good space to work in that topic, for sure. The other point is also the process for ASSB. I think it's key because we will change of processing technology. And of course, the dry process is by far the best solution, but it's more difficult. So probably in a first phase, that could be a solvent-based technology. Our process is key. Recycling, even if it's difficult to have an idea a priori, let's say, but I think it's very important to take the point into account from the very beginning, to be sure that we will not have problems, even if it's in 15 or 20 years. Okay. And the last point, I think, in such challenging new technology, collaboration between all the actors of the value chain is really key, because it's impossible to have a success alone. So let's say we have to collaborate with partners, and in that frame, the initiatives like at IPCEI or Horizon Europe are really key to help us to work together and to find a solution for that challenging technology.
That's a big program. So I think it's going to keep us busy for many years to come. So
yes,
you just need to find the solid state battery scientists and chemists that are being trained to make sure they come to the companies. That's going to be also a big challenge. Access to talent is going to be
indeed
a potential headache. But there's a work for those who want to be active in solid state battery. That's my key takeaway, is that there's a lot to do. So all good forces should be there. I also want to thank all the presenters for the morning. Sorry for some of you that I rushed you with the time, but the purpose was to have as much time as possible for everyone to speak, and I think we succeeded. Now quickly about what is coming next. We will be starting again the session at 1:30, focusing on European projects. The master of ceremony will be Walter IJzermans from BEPA. And at the end, I will work towards making my own takeaways. So that's something that we will do from 1:30. So you have about 1 hour to do all the necessary work, and we will reconvene at 1:30. So see you very soon. Bye-bye, everyone.
Bye-bye. Thanks.
Thank you. Bye-bye.
Bye-bye. Thank you.
Bye.
Good afternoon, everybody. Welcome back to the second part of this workshop. We are waiting for everybody to reconnect again and see the numbers going up. So it's encouraging. Everybody is taking their lunch and a coffee and is settling in. So I put on the screen quickly the overview of what's to follow. So we're going to have a nice look at the different some different projects that are going on in the space of solid-state battery materials within the Horizon framework programs. And actually, we have 3 projects that come from the LCBAT 2019 call. So they have all started in various points in 2020, going on to 2023. And they'll be followed by a new batch of projects that have been funded under the first work program of the BAT4EU partnership, and we're part of the 2021 work program there, and therefore have started only recently. So we can both have a good mix of projects that have already seen some challenges, overcome them, hopefully, can share the lessons learned, and we can talk about the ambitions and the future challenges that will be faced by the projects that are still need to be still on the point of on the brink of starting, and we'll tackle those challenges head on in the upcoming days and years. So if I look at the speaker list, it's roughly as the same as communicated. There's just a small switch at the latter part of the program, where now we will first hear after the coffee break from the seatbelt program, and then they will be followed by the Lena project due to some personal time constraints. I don't see Martin yet in the list of panelists. I've just sent him a reminder to join, so I hope he can make it. Otherwise, we'll go on already with Guinevere, if that's okay for you. Then we can start with the ASTRABAT project. So this is one of the projects that was funded on the LCBAT 1. The title of the call was Strongly Improved, Highly Performant and Safe All-Solid-State Batteries for Electrical Vehicles. So that's a quite ambitious title for the call, and we'll see how ASTRABAT has fulfilled that. So Guinevere has a PhD at from the University of Oklahoma. She got it in 2009, and has worked in many prominent research groups like the University of Padua, the MEET Battery Research Center at the University of Münster, and the Helmholtz Institute in Ulm. And now she's at Fraunhofer ISC, group leader on lithium-ion technology, and I think the project coordinator of the ASTRABAT project, or the technical coordinator. Now I'm doubting myself, but Guinevere, if you you can introduce yourself and the project.
Let's say neither.
Yeah.
We're one of the core material developers within the project, and so one of the, let's say, the core group.
Yeah. I don't see Martin in the panel list, but in the general attendee list. I don't know if that's a problem or not. Otherwise, we'll Gemma can maybe look into this. But let's start with Guinevere, and then we'll try to sort the situation with Martin in the back. Go ahead.
Okay. Can you see my screen in full screen?
Yes, perfectly.
Okay, so thank you for the invitation to present the ASTRABAT project here. As previously said, my name is Guinevere Giffen. I'm a group leader at Fraunhofer ISC, and we're one of the sort of core partners within the ASTRABAT project. There we go. So as already mentioned, this project came out of the LCBAT call in 2019. We have 14 partners out of 9 different countries, which more or less make up most of the value chain for this particular project. Our project is supposed to end in June this year, but as many of the calls or many of the projects at the moment, we'll see how that all turns out. In terms of the general objectives for Astrobot, the main goal revolves around finding better cell architectures, particularly for all solid state electrolytes, to design well-suited electrolytes for the new high energy electrode materials, and to develop and assess compatible processes for mass production. So you can see here on the bottom some of the key points that we hope to address and are working on, certainly in the third year of our project, to address for these particular objectives. So for example, we were looking at coming up with materials based on hybrid polymer electrolytes, and also then to combine those with the novel active materials. In this case, we're looking to make a solid lithium ion cell, a solid state lithium ion cell. So we're pairing it with a silicon anode in this case. All of these materials, we were looking for processes that could be compatible or easily compatible with large scale manufacturing. And so we want to validate that at a pilot scale within the project with the goal of a 10 ampere hour E-type cell. In addition, we want to look at alternative cell architectures, either or and for E or P-type cells, and these should be on the pre-prototype level. We want to evaluate the safety so that we have basically the combination of an efficient cell architecture with improved safety demands. And then finally, look along the whole value chain, so including aspects from eco-design, end of life, and also start looking at particular aspects of recycling for these solid state cells. So now I'm going to move slowly through some of the results that we have within the project. And along the way, I'll put in some of the challenges and some of the challenges that are maybe still ongoing for this work. So the Astrobot cell is intended to basically take advantage of the strengths of different electrolytes, and therefore we've basically designed electrolytes for the anode side and for the cathode side. This allows us to more easily reach our KPI in terms of electrochemical stability window, because then we basically can have one material that's has a window down to 0 volts, compatible with the anode side, and another material then that's compatible with the cathode side and goes up to 4.5 volts. In both cases, we had the KPI for conductivity of 0.4 millisiemens per centimeter. And so here is some conductivity data for both the anolyte and the catholyte. In this case, we're working with formulations that are containing a smaller amount of plasticizer, so somewhere between 15 and 30% of ionic liquid. So this, in the case here, this plasticizer doesn't have a high evaporation, partial pressure. We shouldn't have any significant impact in terms of flammability, but this is certainly one of the things that we're going to be doing in the last part of the project as part of the safety evaluation, is really to understand what is, or are there any safety aspects associated with such hybrid electrolytes. Hybrid in this case is also going to contain LZO. So we're going to be using a certain percentage of LZO in the catholyte. This catholyte material is being developed by IKTS, so Fraunhofer in Dresden. And here you see a little bit of the characterization of the material. So they've got conductivities of 2 to 3 times 10 to the minus 4 Siemens per centimeter. And this is now for a particle in the nanometer range, so about 210 nanometers. And the reason for this particular particle size will become clear a little bit later when we talk about some of the technologies using to the technologies we want to use to produce electrodes. This particular material, which has a surface area about 37 meters squared per gram, has then been incorporated into the anolyte formulation. So here you see an example of a freestanding film that has been produced by Daikin Chemical Europe, containing a fluoropolymer, a lithium salt, the ionic liquid, and the LZO. And so the idea is then that this can be used as a separator within the battery cell. As one of the other aspects, we would like to investigate an architecture where you have, instead of LZO particles, instead you have LZO nanorods to basically help tune the percolation pathways within the electrolyte. So here, LATAT in Spain has been working on coming up with methods to produce these LZO nanorods using electrospinning techniques. In addition, we also have Warsaw University, who has come up with two new ionic liquids and 3 new lithium ion salts that can then be also integrated within the electrolytes themselves. So here are a few results concerning the silicon anode half cells. That's the work that we are doing at Fraunhofer ISC. The silicon has been developed by nanomakers. Here, 6 different grades of silicon were optimized and investigated by CEA, supporting nanomakers in this effort. And then we took those silicon particles and made them into aqueous processed electrodes. So you see here in the figure on the left, if I can just get my pointer, there we go. In this set of figures here, 2 different electrode loadings. So a more, let's say, a lower mass loading and a bit higher mass loading of 2 milliamp hours per gram of silicon. Oh, that should be probably milliamp hours per centimeter squared. And then basically what we do is we can coat the electrolyte on top of these porous electrodes and fully infiltrate the electrode mass. So here you see in the middle simply the SEM picture, and then with the EDX, where the fluorine signal is coming only from the electrolyte. And you can see even here with the higher loadings, you can basically infiltrate the electrode all the way down to the current collector. So to a certain extent here, we've drawn on aspects of lithium ion production. So using standard tape casting of electrodes. The challenge in this, in terms of transferring it to large-scale production technology, is basically you have to consider the coating of the electrolytes is going to have to be done in low water conditions. So basically, you're looking at, is this something that has to happen in the dry room? As part of the project, we are looking or evaluating how exactly such a manufacturing plant needs to look like, but this work is still ongoing at the moment. In terms of then the function of these electrolytes, or sorry, of these polymer-based anodes, we've looked at 2 different formulations, one based on TFSI, one based on FSI. In both cases, we have about 15% of the ionic liquid included in the formulation, and we're able to get about 100 milliamp hours per gram of silicon. We are limiting the capacity here, so we weren't trying to cycle the whole capacity. And interestingly enough, you're able to actually get a better cycling performance with higher amounts of silicon and lower amounts of binder. In terms of the FSI enables a better rate capability as compared to the TFSI system, although with a slightly lower capacity retention. The main challenge here that we're still working on is basically increasing the loading of the electrodes. So as I mentioned, we're looking at different cell architectures and processing methods. One of the things that we will look at on the pre-prototype level is using printing, 3D printing methods. So for example, inkjet printing to produce a specialized architecture. Part of the work here has been going through and designing inks for these printing applications. So on the left side, you see printability tests for an NFC-based ink for the cathode. This is simply a tape casting of this ink, but the first printability test results are ongoing at the moment, including more detailed patterns and so on. On the left side, we also then were developing an LLZO-based ink for the separator. This was the reason, as I mentioned above, that it was important to have a very small particle size, because of course, in both the case of the NMC and with the LLZO, if the particle sizes are too big, then you'll have clogging of the printhead nozzle. So here is more or less the dispersibility tests and the sedimentation tests for the LLZO ink with a rather nice stability over the time here with something that's rather easily dispersible after the fact, as if it settles out a little bit. So there are certainly a lot of opportunities for using inkjet or printing in general for lithium-ion batteries or solid state, but there are certainly challenges that have to be solved, some of which we're certainly addressing within the project. So for example, you have to worry about things like particle size, distribution, because they both go back to issues associated with nozzle clogging. You have to have an ink with appropriate rheological properties, so it has to be printable. But at the same time, it has to have the right viscoelastic properties so you don't have issues associated with strain hardening. And in general, the formulation of a suitable ink is always going to be a trade-off between printability and battery performance. And even the case that you have a well-formulated ink, in terms of printability and in terms of electrochemical performance, this does not always in the end ensure a stable drop generation. And so this is something that is certainly complex, but hopefully by the end of the project, we'll have also here found some solutions to some of the challenges that we have faced and as are presented here. And then finally, for my last slide, in terms of certification and standards, we've been also working in this area. So here, Lamartov in combination with ELAF to look at some of the new aspects that you have to consider. So particularly in terms of the EU legislation, the new regulations, various safety standards, and so on. And then on the other side, we've also been looking in terms of the LCA. So the Martov has a live LCA-based eco-design tool that allows us to look at materials and properties to basically consider criticality of material selections, resources consumption, carbon footprint, safe by design, and recycling by design. And so in the first part of the project, we've looked at a variety of different materials in comparison with each other, a variety of different processes, and we've basically seen that the choice in the end is always going to be a selection between the best trade-off of sustainability in terms of performance, but wherever possible, we've allowed this eco-design tool to help guide us in terms of material or process choices when the performance would allow that. And so with that, I will end here. Thank you for your time and your interest in the Astrobot project.
Thank you, Jennifer. You're perfectly on time, so that's fantastic. I just one question popping up in the Q&A. Why? Yeah, is there an explanation why the printability and the battery performance are they a trade-off, and is this necessarily so, or is there a way, or is there a way to think that we actually could merge those two or combine those two in a win-win?
At the moment, I would say as long as we're not designing materials particularly for printing applications, it is going to be a trade-off. This is certainly going to be a task that has to come in the future of designing the materials in the first place so that they have the proper properties to be printable. So one of the challenges, for example, with the LZO material was reproducibility of the ball milling process. Because of course, when you synthesize the materials, they're much larger, and then you have aggregate formation that leads to nozzle clogging. If the material synthesis enables you to design particles with sizes in the first place that do not cause problems with clogging, and you can have the electrochemical performance, then you don't have the trade-off anymore.
Yeah, and I think at some point, then if you want to take the next step, you also look at scalability, which adds another factor, and then the sustainability as well. So it's still going to remain trade-offs, but maybe between different
exactly
aspects.
Everything is always a trade-off. It's just which trade-offs can you live with, and which ones do you really have to design for that purpose.
Yeah. Question from Maya Wilkman is, what are the benefits of printing versus coating and cutting? So it's like, what's in terms of the other trade-offs, what's the benefit of the printing method?
I think part of the point here was it enables new architectures to be examined. So for example, maybe to optimize spacing, to allow you to get higher, possibly higher power densities through shortening diffusion pathways, for example. So it allows you to go to more, let's say, tailored cell architectures.
Yeah. And as a takeaway from your projects, well, you're still in the middle of it, so it's still a lot of ongoing work.
Yes.
But what are already you see some challenges that you now have come across that you think, okay, we're not gonna take this here, we need to take this further, some park it for now, but take it somewhere else that you want to take up in the future?
Certainly there's a lot of them that we hope to solve in the next the next period of time. I think one of the challenges certainly going to come on the printing side, particularly in what is the most appropriate method for printing. So will it be inkjet printing, or will there be other methods that may work better for the particular inks that we've formulated? I think there's always going to be improvements possible in terms of the electrolyte. But I think that's a general point. As I saw from the morning sessions, there really hasn't been one main electrolyte that has crystallized as the electrolyte, and I think this will also be the case within even within the polymer game. I mean, when we listen to the next presentations, we're going to see other various polymer-based electrolyte variations, and I mean, you're going to have somewhere between 4 to 6 different electrolytes, which is the best.
Yeah.
And so I think there's always going to be optimization possible there.
Yeah, clear. Thank you so much for now. Let's move on to the next presentation and discuss a little bit more about the ongoing challenges at the end of the session. Thank you, Guinevere. Let's see. Now we have Martin visible and hopefully also audible.
Yes, I hope so as well.
Yes, exactly. Perfect.
Great, Wouter.
Martin, welcome with us. You have a Master of Science in Engineering and a postgraduate degree in Business Economics from KU Leuven. You started your PhD in 2003 at IMEC Leuven and have Fabrice, you're not unmuted. And you have joined the electrochemistry department in 2017, guiding several different projects and also guiding the team towards industrialization, which is a topic that we might touch upon in the final session. But would like to give you the floor now to show what's been done in the Solidify project, which challenges you have faced, and which ones are still to be tackled.
Great, thank you, Wouter. Thanks for the invitation and a nice introduction as well. So indeed, I'm in the electrochemical storage team at EMIRI, so basically the battery team at EMIRI, where I'm at the moment the team lead, overseeing the projects and the activities. Thanks a lot. I hope I'm sharing my screen, that everybody can see it. So I will talk about the Solidify project, which is indeed a project from the same call as Astrabat.
I don't see it at the moment, Martin, the screen.
Then I will have to retry.
Yes, now we see
yes.
it. Okay.
Thanks a lot. I'm not so used to the Zoom software. So indeed, Solidify, so project where Philippe Verreken, our scientific head, is the coordinator, and I'm here presenting some of the results. So if we take a look to, yes, the Solidify project, we started something like 2-3 years ago, and IMEC is indeed the coordinator, with of course a lot of partners all over Europe to contribute to the several work packages. Yep. So the general concept of Solidify is given here in this overview picture that we always show if we present this project. Basically, we base ourselves on an electrolyte that can be processed from a liquid state, and it solidifies after impregnation in, for example, the cathode. So we can impregnate the cathode with a liquid phase. It can solidify to be solid, and then we combine it with a lithium metal anode. So that's also different from Astrabat, where silicon anodes were evaluated. We really focus on a lithium metal anode. And so we have different activities, both on the materials, cathode, solid electrolyte, lithium anodes, also on the integration into cells, of course, and then activities on simulation, measurements, and also outlook. I will mainly focus here a bit on material upscaling, so basically the different cell components that we are taking a look at, and cell assembly. Towards outlook, I will be rather limited here in this talk. So directly, if you take a look to the challenges that you generally see when you want to aim at batteries for mobile applications. Typically, we always want a lot of high voltage to have a high energy. We want a low volume and a low weight, again, to have this high energy. We want a lot of cycles, and we want the high C rate during charge. Typically, these are the requirements that are coming back for all these mobility applications. And this means that you have to work on all different cell components to make these things possible. I'll bullet point here the main challenges that need to be tackled to enable these requirements. You see there are quite some challenges that need to be tackled then both on the cathode side, on the lithium side, and also on the SCE side. So quite some things need to be tackled to be able to make all these things possible. If you then take a look to what have we done already in the Solidify project, let's first take a look to then the solid electrolyte separator. So what we want to do there is really create a solid electrolyte separator sheet that you can process as a separator sheet in more conventional liquid electrolyte batteries. We have evaluated here 2 different approaches for this nano SCE solid electrolyte. One based on an oxide, silicon oxide template matrix, one based on a polymer ionic liquids composite material. So both different materials, both of them in combination with different ionic liquids as being the active electrolyte in the separator sheet. And from this comparison, we have selected at this moment the pill-based, the polymerized ionic liquid-based solid electrolyte to take it further to the demonstrator cells. And the selection there was made basically on the fact that we want a strong and thin separator sheet to be able to go to these higher watt hours per liter. You need to be able to have a strong and thin separator sheet with still decent conductivities. And to aim that, we selected this polymerized ionic liquid composite, which proved to be best to go to thin and strong sheets. So that was the first selection that we made for the solid electrolyte separator one. What is ongoing in the composite cathode work package? There we make a discrimination between two generations of the demonstrator cells. In the first generation, we are focusing on NMC 622 particles, and we take a look to different coatings on this NMC 622 particles. So the particles themselves are coated by one of the partners. It's a collaboration between Umicore and Delft EMP, who are doing ALD coatings of these NMC 622 particles. We were comparing different coatings with the goal to enable the aqueous processing of these particles in cathode slurries and in real cathodes. Based on those experiments, there also we made one selection. So one of these coatings has been selected, has been made by Delft EMP, and we selected one of them to be the best one, to be best compatible with aqueous processing in terms of lithium leaching and cathode performance. And so that one has also been selected and is now being put in our demonstrator cells as well. If we take a look forward to what will we do in generation 2, that's really towards the last quarter of the project. There we will also integrate NMC 811 particles, active material particles. So also their coating of these particles is ongoing. Similar coatings as what we have learned from the work on NMC 622. So here we apply them on NMC 811 as well. And so there also the best coating will be selected. And we are also there working on different ways to make higher loading cathodes. So it's not just a single standard cathode coating that we make under standard cathode coating. I understand making a slurry and just coat that. No, we are also looking to different ways to make cathodes with a higher loading, again, to enable these higher energy densities for the battery. And so 3 different options are there evaluated. One is a single step where we really combine the solid electrolyte and the active material in one coating step. Taking a look to an open current collector, where the current collector is rather a foam or a mesh instead of just a foil, and also to what we call trenched cathodes. And basically that's a way of coating the cathodes in a way that the porosity has a certain preferential direction, allowing to go to higher, thicker cathodes with a higher loading and still decent C rates. That work is basically ongoing. Selection of a coating needs to be done, and also final selection of the coating method has not been made, but that are things that we will demonstrate by the end of next year. For the tin lithium anodes, so basically what we do there, we start from a lithium evaporated on a copper foil. So it's a tin lithium by evaporation, deposited by evaporation in the range of 20 micrometers, and delivered and developed by one of the partners. That's Zitrawe, basically. And on top of that tin lithium foil, we also there apply a coating. We call it here an artificial interface layer. Also there we made comparisons between different layers, different stacks of layers even, to see which one is best suited to protect the lithium from interaction with the electrolyte, and also to enable long cycling without loss of this thin evaporated lithium layer, this thin layer of excess lithium. And basically there as well, we have made a selection now. It's called here number 5, which is a combination, it's just stack basically of different interface layers, again, to enable high cycling. Basic graph is shown here, the comparison between just an untreated lithium and a treated lithium with this number 5 of interfacial layers, enabling more cycles, and clearly showing there an improvement, which is now being used for the demonstrator cells of Gen S1, and possibly an improved version will be used for generation 2 by the end of next year. What we also want to enable for the second generation of the cells is an textured lithium surface. The goal is to enable high C rates, basically high current densities during plating and stripping, and mainly during plating, as that is the charging step, to enable high current densities, effective current densities. We want to study the effect of texturing of the lithium anode, because texturing allows to have locally a smaller current density, and in that sense still have smooth uniform plating without and still be able to go to high current densities. That work is ongoing at the moment as well. No results published or shown here, but it's something that we want to integrate in the second generation of the cells. And then basically cell integration, where are we there at the moment? So the first generation of cells, 2 different sizes are being made or are in the process of being made. The ones of the small densities, basically these demonstrator cells have been made over the last 2 months, and so results there are available at the moment. We are now focusing to also make these larger cells to demonstrate indeed that the same processes can also be applied on larger cells, on cells with different stacks of electrodes as well. So that's for the first generation. Second generation is for the last quarters of next year, based on the second generation of the cell components, as shortly mentioned in the previous slides as well. And then also I want to show here one results or one ongoing activity, one ongoing task from the testing and simulation work package as well. As we all know, during cycling, during charging and discharging, there are volume changes in our cell. For example, the lithium metal anode that we use, it grows and crimps during plating and stripping. If the plating and stripping is not completely uniform, we can have bumps or dendrites and pits and valleys, which risks to result in bad electronical and mechanical contact between the lithium metal anode and the salt electrolyte. So that's why in this work package, the effect of pressure was studied with a dedicated pressure setup to be able to apply different pressures with a high precision and measure the pressures with a high precision. What is shown here as well, by the way, is an example, a picture of the solid electrolyte sheets, separator sheets that are being used now for the first demonstrators, giving an idea on how it looks in reality. So if we take indeed a look to these pressurized results, you see, for example, indeed a strong impact of the pressure on the applied performance, in this case on symmetrical lithium cells, where a certain pressure is applied. And now we can take a look to the cycling behavior. You can see different changes, both in what we call the stabilization time. How long does it take to come to a stable resistance of the cell, given in this plot? So you see at an increased pressure, you come to a faster stabilization, steady state situation of your cell. And also as you increase the pressure, you can see that the stability during cycling, during polarization is increased as well. Here presented for 2 current densities of around 0.1 milliamp per square centimeter. So that were some intermediate results shown here for the Solidify project. Coming back to these challenges that I presented at the beginning. So quite some challenges on different topics, on different requirements needed for mobility applications. What we noticed during this project, what was already a task in this project, but what we are still noticing and are still aware, and what we think is gaining even in importance, is that for several of these requirements, several of these tasks, you need a control of the interface between the different materials, control of the interface between the cathode and the electrolyte, between the anode and the electrolytes, just to be able to make these cell components work as we needed them. So we do really think that this is a topic that has value within this project, but we believe also afterwards, just to be able to control the interface, to protect the electrolytes against the anode and the cathode, to protect electrolytes, to protect cathode and anode against the process environment, aqueous process environment, yes or no dry room conditions, and also this artificial interface. It needs to survive a lot of cycles. It needs to have a long lifetime, which means it also needs to be mechanically strong and self-healing. And to put all these things in one artificial interface layer is not so straightforward. So that's a topic of interest, we believe. And basically, that already brings me to the end of this presentation. And I will give the word back to Wouter then.
Thank you, Martin. That was very enlightening to see how which challenges you face and how you are planning to solve them, and that you actually have come to the conclusion that it's even more important than you maybe thought in the outset to be in control of these interfaces. For me, a question is how is the manufacturing outlook for applying those interface layers? You now see it's an important thing. Is it are we ready for it to manufacture, or just also we need to make advances there to get it ready?
Yeah, good point. So for the interface layers, different processes are now used within the project. If we look to the cathode, I mentioned different coatings of the cathode particles there. At the moment, that's done by an ALD process of Delft EMP, really on the particles themselves. So they indeed have ALD tools that they claim are able to scale up the process of ALD deposition on large batches, large amounts of active material particles. Alternatively, one could also think of doing ALD processes on a cathode which has already been coated, where you then need to deposit the coatings into the porous structure of the cathode. Might be less straightforward, might be at first instance more complex to realize that on an industrial scale. Nevertheless, we can imagine also there are options to look, for example, to spatial ALD and technology that has been used in, for example, high throughput solar cell production lines. So one can imagine that also there are possibilities if the concept of ALD on an already formed cathode are proven.
Okay, thank you. Now I look forward to the future results where you're heading, and see if we can see the next generation of the validation cells and see how you function there. So good luck on that. I don't see any further questions, so I'll thank you for now, and let's move to the next project. I'm going to talk about Safely Move now. We have let's now move on to the sort of next batch of projects. So we now have looked at the LCBAT1 projects, and now we're going to look at the one that come from the 2021 BAT4EU World Program. The title of this of the call was Advanced High Performance Generation 4A 4B line lithium-ion batteries for supporting electromobility and other applications. So it was really the prolongment of what we just saw. First up, we have Roberto Minco, who will present the Psionic project. Robert is a research professor at the National Institute of Chemistry and a professor at the University of Ljubljana. He is head of the battery group at the National Institute of Chemistry of Slovenia. Robert has obtained his PhD in material sciences in 2002 from the University of Ljubljana, but is a true European and also spent several months at the Charles University in Prague and the Technical University of Denmark in Copenhagen. And since his PhD study has also been around also to the university in Jouvian in Amiens, and is very active in the Batteries Europe and Battery 2030 Plus programs. So Robert, what are your plans, and what are you planning to tackle in the Psionic project?
Yeah, thank you first for the invitation, and actually thank you for organizing this excellent overview of what is going on European level on different battery, solid state battery activities, and that's actually excellent work or excellent meeting that is followed by meeting that was last week in Frankfurt, organized by Jürgen Janek on solid state batteries, and actually challenges that I'm listening, the challenges that some European projects have. They were also discussed there at this meeting, and I agree with the previous speaker from Safe Live Move. Actually, those are the major challenges, which are not only within the project, within the projects, but they are actually more general worldwide project challenges. So Psionic was designed around Blue Solutions and their technology. So, and actually we failed to be granted in the first call. So we resubmit this project in the second call and with coordination from Blue Solution. And actually the scientific coordinator of the project is Margot Lecuyer from Blue Solution. And she's, and actually that's also Blue Solution is also the main motivator and then main promoter of the activities within this project. So main partners, we can be divided into the academic partners coming from Torino, Ljubljana, Naples, Uppsala, Münster, and Amiens. And then we have two SMEs, Acurec, which is who is responsible for recycling and specific polymers for, of course, for design and synthesis of larger batches of polymers. Renault is involved in this activity, and also Armor as a provider of thin film foils, especially for specially designed current collectors for all solid state batteries. And of course, I should not forget again Blue Solution as a part of this consortium. Clarence actions are project management, and BSF is associated partner. Actually, we have through that line we have access to the NCM material, high nickel rich NCM material, which is planned to be used within this project. So what is our main objective? Our main objective is to design all solid-state battery prototype cells with solvent-free and cost-effective extrusion process. So this is not of surprise, since extrusion process, we know all that this is a specialty of Blue Solution, and they have already industrialization of all solid-state batteries with LFP, but now we want to still keep this metal anode and the processing, or we want to improve even the processing of metal anode and protection of metal anode, and we want to move from LFP to NCM cathode material. And for that, actually, we will need to optimize the design of polymer electrolytes and also polymer electrolyte interfaces. So we are aware of these challenges, which were actually mentioned before, about the lower ionic conductivity, about the possible additional resistances on the interfaces, and that everything limits the power, that limits the cycle life. We are aware that lithium metal anode might not be really stable for several thousand of cycles, but with some modifications, we still have a roadmap how to reach and how to improve. Even nowadays, Blue Solution activity, which where they can actually show more than 2,000 cycles reached with lithium metal. So for that reason, we want actually to use very thin lithium metal. So to be really on this part of the of this figure, and using thin lithium metal, so we will rely on the already on methodology of extrusion of lithium ingot to the lithium metal foil, which is available at Blue Solution, and approximate thickness that we will address will be between 20 to 30 micrometers. So those actually such foils were already distributed among the partners. So we can obtain that foil. Each partner obtained that foil. And they are now tested already in the labs. And as I said, yeah, the main message is actually the main activities will be also the interfaces, and that's why interfaces actually what we want or what we plan to enable this application of high nickel-rich or nickel-rich NCM is this will be enabled through thin homogeneous coatings of NCM particles with single ion conductive polymers. So the idea is to apply coatings which are of thickness 1 micron or less. With that, actually, we protect or degradation, we protect the direct contact, but we actually add additional interface, we add additional phase which has lower conductivity typically compared to the amorphous PO that will be used as a main electrolyte in the cell. And but by minimizing the quantity of single ion conductive polymer, we will actually control these parameters, and we will also try to minimize the impact of single ion conductive polymers on the overall price of the cell. Yeah, so the processing will be, as I said, through extrusion process, so it will be solvent-free. We will go through 3 generations of cell, a so-called generation 0, which is already ongoing research within the Blue Solution, which is and this cell actually this generation 0 is already ongoing right now, and the aim is that we bring all the labs that are working on the polymers and that are actually working on the lab cells. We bring all the labs on the same nominator, so that all of this round-robin test that is done by all the labs, and that we know how to get the same results with using the generation 0 material. Then we will move to the generation 1 and 2, and with that actually we will go through to solvent-free and also truly solid-state batteries, which are planned to be done within the generation 2. And of course, yeah, we want or our aim is those cells are not only taken by electromobility, but there is a planning towards to 2030 how these cells will also impact on the climate neutrality and green energy transition. Basic objectives of the project are there are 7 objectives, specific objectives, and as you can see, we are actually aiming to design this 4.5 volt battery operating at 4.5 volt. We have identified polymer, single ion conductive polymers that are capable to reach such high voltage. And then actually, yeah, and the key KPIs for this specific objective are classical one taken from set plan. So like we heard, but those KPIs can be challenging. So they were setting in the set plan, but as we heard from other projects, that might be challenging. And this development will go through different generation of cell or different size of cells, from 10 milliamp hour cells to 1 amp hour cell, and then finally around 55 amp hour cells will be produced for each generation by end of this generation cycle. Specific objective number 2 actually explains use of thin lithium metal. As I already mentioned, production is already ongoing, and lithium metal can be distributed by Blue Solution. But of course, it is coated with the technology that is used right now, and we want to update this technology with new coatings, which will actually enable even longer cycling and maybe prevent some dendrites. That there is a problem in, as I understand, in other projects. Coating of NCM is with single ion conductive polymer. That was what I already discussed, and yeah, the thickness below 1 micrometer, and overall aim is to have a more than 75% weight percent of cathode material within the catholyte, so with this composite cathode. Then design polymer material interfaces is the third specific objective, and here emphasis is on fast kinetics to reach this high power, which is actually requested by set plan, and which is also challenging. And then the specific objective 4 is improved thermal stability. So we believe that this can be achieved through the amorphization, and so with that also we can have a amorphization of PO, and with that we can have then also better conductivity. And for each polymer, we are planning to synthesize approximately 50 to 60 kilograms of polymer, so that we can really enable the production of these 5 amp hour cells with the numbers between at least 50 5 amp hour cells. Safety hazards level 2 according to EU CAR. And then we will go also through LCA resources assessment, LCA performance, recycling process. So here are also some ideas of some activities will be oriented towards to the recycling, and recycling in the way just not the direct but recycling on the component level to find out maybe if it's only necessary to exchange metallic lithium anode and continue cycling with a catholyte that was maybe cycled for several hundreds or even thousand cycles. And then also the cost reduction. I already mentioned our focus on the minimizing amount of single ion conductive polymer, but also minimizing amount of, or going away from all liquids, so the drying process will be avoided, and so on. So there are several steps where we can actually implement this activity on this specific project. And the major aim is actually to have a cost on the cost cell level is approximately 75 euros per kilowatt, but that was actually predicted before all this crisis, energy crisis that we are faced right now. This is more or less summarized on this slide, how we are going to get all the impacts. As I said, most of the KPIs are taken from the set plan. They are quite tough KPIs and can be challenged. And maybe for some of KPIs, it's a question whether we don't need to go back to even to the materials that are produced by active materials, for example, BSF or Umicore material, which should be specially designed for the application which we are targeting, or for the polymer that we are actually planning to use. The work will be done within the 7 work packages. The first one is about the requirements. The second and the third are about design. I forgot to mention that there is also a lot of modeling where University of Naples and Uppsala universities are involved. Then we have in work package 4, we have validations by actually making different size of prototype cells. and all the tests, and then we go to the recycling, second life, and safety measurements, and also LCA, and actually that's is complemented by project management and dissemination, experimentation, and business plan. So that's approximate roadmap that we started from in July 2022. And now actually we are somewhere here. So we are in this first Serpentine. So we are facing some challenges, but so far they are manageable. So it was quite challenging to bring all the labs to have this round robin test repeatable and manageable by all the laboratories that will work on the batteries, lab size batteries. But we have also plans what to do after June 2026, when officially project will be finished, if there will be no pandemic or whatever, postponing the project duration. And also, of course, this plan is to move to the higher tier level. And since the Blue Solution is coordinator, they want to have this technology, and I think this plan is quite reliable if we achieve at least partially KPIs that were promised within the project. So just to show you this activity on round robin test, this is actually for that we are using nickel manganese iron phosphate material. And actually, we with the material from Blue Solution, with polymers from Blue Solution, we were all managed to get this around 160 milliamp hours per gram capacity, or even lower than when going to the higher C rate, but with high repeatability. And also, we are cycling symmetrical lithium cells, which give repeatable results among all partners and according to Blue Solution expectation. So with that, I would like to stop this, and just once again, is a consortium of several partners. NIC is just a work package leader of work package 3. Coordinator is Blue Solution, but also all other partners are covering the wide aspect of a value chain for all solid state polymer, all solid state batteries. And thank you for your attention.
Thank you, Robert. Very clear what challenges you want to tackle, and yeah, they're in line with what just been seen. Is just taking a next step. I was wondering, I saw in the slides you have that you also look at second life. Is that traditional second life, so after a mobility application, or
that's traditional. That's traditional second life, and also there is one task where we plan to disassemble cell and assemble it back with the fresh lithium.
Okay. Yeah.
So it's like a half recycling, half cycle life. So it's quite it's difficult to say where does it fit. Yeah.
Yeah, exactly. So half direct recycling of the. Okay, thank you so much. I don't know if there's any other questions for Robert at this point. But it's very interesting to see you start with the current generation and trying to see if you can change the chemistry and get better results. The last second point I had written down myself was you're targeting very high voltage, 4.5 volts. How do you see the challenges posed by the previous speaker in safely move on that are posed by high voltage? Do you think you can tackle those within the project?
I'm not polymers specialist. That's not my specialty, but according to specific polymers, according to University of the Politecnico Torino, they have already polymers in the lab. I think papers are already published where they can show this high voltage stability. And now, of course, we need to transfer this to the NCM cathodes. We need to, actually, it's a more engineering approach than some basic approach that it needs to be solved.
Okay.
Yeah.
Good.
So according to them, it is possible. I need to trust them.
Yeah. Exactly. Thank you so much, Robert. I don't see any other questions. So yeah, there's another one. just popping up. Will it be possible to reassemble the cell with new lithium anodes with the polymer electrolyte? So how is that reassemblage gonna look like?
Yeah, that's the idea, especially if you are actually, there are two polymers. So one is single ion conductive polymer or on NCM cathodes, and another one is amorphous PO-based polymer on the lithium metal. So I do believe that at least in small cells, we will be able to demonstrate that by the end of the project. But of course, all the work will be done in dry room or in glove box. So it's we plan to demonstrate this on these small cells, 100 milliamp hour cells, or at least 1 amp hour cells.
Okay, great. Thank you, Robert. That was a very good presentation as well. And with that, we have come to the coffee break. So if you want to get a refreshment, please do. We'll reconvene at 3:05 for the final two presentations and the panel discussion to finalize this. So see you soon in 15 minutes. Good afternoon. I hope everybody has taken their refreshments and is ready for the last part of this session. Welcome back, everybody. I will just quickly put the slides on the screen so we know what we are gonna look at. So first, we're gonna have two more presentations on the same call topic as just presented by Robert. First will be the seatbelt project and then the Helena project. And then we will go into a panel discussion with short Q&A on the challenges of solid-state battery research in Europe. And then afterwards, we'll have a wrap-up with Fabrice Stassin and Javier Olarte from CSA Energiegune and leader of the EMIRI Batteries Working Group. So without further ado for this this session, let me give the floor to Irene Villa Luenga, who is presenting to us the seatbelt program. Irene has a very international background. She has her PhD from the University of the Basque Country, but also spent time in Sweden and at the National Institute of Advanced Industrial Science and Technology in Japan. And in 2011, she moved to CSA Energiegune as a postdoc, but then afterwards moved to Berkeley University in California, and also joined a solid-state startup there. And currently, she works now for the University of the Basque Country and the Polymath Institute as a research fellow, and works as a solid-state battery consultant, and is charge of all things technical for the seatbelt project. So Irina, very happy that you could make it, and looking forward to see what you are tackling in this project.
Thank you. Thank you for very kind presentation. Yeah, so I am going to talk a little bit about the seatbelt project. So okay, yeah. So Didier Thibault from the CNRS, he's the coordinator. I am part of this project, so more leading the work package 2 that is related to the materials development of electrolytes of this project, based more in hybrids. So the seatbelts already has a website, so you can take a look. I mean, for more information here, and as well contact Didier or me if you have any question as well. So this is just a reminder of the call that we applied. So the scope, I mean, was to solid electrolyte, I mean, cathode materials, anode materials, like a novelty, new materials with a controlled thermal runaway, creating no propagation designs, and based on lithium metal based anodes. Was this called more for generation 4B, so related to the solid state lithium metal based anode materials. And then so there are, I mean, several, I mean, bullet points that Silvet projects cover. So the challenge of the design of a new materials in order to increase and develop, I mean, high energy densities batteries, work with the lithium metal and coatings strategies in order to make compatible electrolytes, or to have, I mean, stable SCIs, manufacturing and handling lithium metal in the dry atmosphere, solvent-free electron manufacturing, and solid electrolyte deposition. This is something as well that seatbelt project covers, and as well improvement of interface and cell mechanical stabilities. So the objective of the seatbelt is to generate cost-effective and robust solid-state lithium battery comprising sustainable materials by 2026. The TRL, the milestones will be around TRL 5, and the application is going to be for electrical vehicle and stationary industry. The idea is to develop and to use sustainable and recyclable materials based on hybrid materials, inorganic and polymers, reaching, high densities, higher than 380 watts-hour per kilogram, and long cyclability higher than 500 cycles by 2026. That this is in line with the European targets, for 2013. We are going to as well to use, the solvent-free methods, so extrusion method in this case. The idea is to combine these methods with the novel materials, so try to reduce, the lithium metal thickness as well, develop hybrid electrolytes, and as well develop cathode active materials without critical materials. That I think this is other challenge in order to reach, higher high energy densities. What kind of materials they are using in these active cathode materials, and then as well thin aluminum current collectors. The cell design is going to be as well optimized by operando atomic disk modeling and machine learning methodologies. And as well, we are in the project, we'll work with the in situ mining instrumentation in order to explore the safety and mechanical deformation to assess the cell safety in real conditions. And as well, the other thing that is going to be explored is the recycling as well for these novel materials, and then try to explore, this recyclability in the whole, I would say, the volume change of the battery. Then the seatbelt is composed by 14 beneficiary partners, 3 affiliated entities, and 1 associate partner from 7 European countries. So I will say, here I want to explain a little bit more the challenge. I think that we can find, nowadays, and what are the solutions, or what are the solution that seatbelt proposed. So if we take a look in the generation 2B or 3A, they are more focusing in the anode based on graphite, silicon, and liquid electrolytes. So these are more commercial cells. However, the energy densities and the gravimetric energy density and volumetric are lower than the target that European target for 2013. So I think, in order to really reach this, the idea is to move, to really generation 4A or generation 4B. So the generation 4A is still as well under development, and it's based on graphite and silicon. And but still, below these values that there are the target, I would say. Then we can find, generation 4B, that this is the commercial cell that we can find from Brew Solutions company, based on LFP as a cathode active material, then solid state polymer electrolyte and lithium metal. This, I think, is for us, or for the idea of this, very, very good like a starting point, but still that as well below, the target that we are thinking related to the energy density is volumetric, and as well for that, the idea of seatbelt is to develop a new solid state electrolyte based on hybrids. and so inorganic electrolyte and polymer electrolytes, working interlayers as well between the solid state electrolyte. That I think when we're one of the challenging hybrid fields is that stability from the inorganic electrolyte with the lithium metals. So the idea in this project as well is to play and to develop new interlayers to be compatible these new hybrids with the lithium metal, reduce that I say before, I mean the thickness of lithium metal, and work with more cheap and sustainable cathode active materials based on double lithium iron phosphate. As well as going to be explore interlayers between, I mean, the cathode and the aluminum current collector, that as well is going to be reduce the thickness as much as possible. This is other challenge that as well we want to try, I mean, to work on. In a cell of the sill belt, the idea is to really reach, I mean, higher gravimetric and densities and volumetric, around 380, 400 for gravimetric and around 1050 for volumetric. This project starts in TRL 2 and goes to TRL 5, and that I say that we'll have additional criteria like a low cost. So for that reason as well, to focus in this new, I mean, double lithium iron phosphates, sustainable. So as well, I mean, these hybrid materials, they are going to be inorganic materials as well, like cheap, sustainable, and polymer as well. And then the target application that I said before is going to be electric vehicles and stationary. So the seatbelt methodology, I want to show here in this figure. I think it's pretty visual. From the cathode size, that the idea is that to develop, I mean, new cathode active materials in order to really improve, I mean, the performance that we can reach, but as well keeping that, I mean, a low cost, and as well, I mean, non-critical materials at the end, like can be nickel or cobalt. And then we are going to use extrusion synthesis, so free solvents. This is like a part of the process lamination, develop as well working in the current collector in order to maximize our performance. And this is going to be complementary with operando X-ray methods in order to study and to understand better, I mean, the all challenge that we can find in our cathode. It can be related to the interfaces between our active material and electrolyte. And then as well, we are going to include machine learning in order to maximize as well. So the compositions that we are going to play, and as well the materials process as well. So from the hybrid electrolyte, we are going to work with the polymers. They are going to be more sustainable, more green. So the idea is to replace this PVDF, so to avoid the fluorinated compounds and work with something that is cheaper and green. Then inorganic electrolyte as well is going to, we are going to incorporate modeling in order to make a screening of the inorganic materials that they are going to, in this case, we are going to be focused more in highlights in order to make, I mean, cheap and as well to maximize the transport properties that we can get. Then we are going to extrude as well these hybrid electrolytes. We are going to work as well with different process. So nowadays we can find, I mean, the typical, when we are talking about hybrids, cell blends. So yes, mix, I mean, the inorganic and or polymer. I think, I mean, there is many challenges there as well related because there is not any control of the morphology, how we can process that. And usually you can find as well voids or there is depends what kind of a polymer you use. If it's inert as well, can be, I mean, like a hot spots, I mean, for dendrites, because I mean, we don't have any like the charge transfer is going to be huge between the polymer and inorganic. So the idea in this, I mean, project as well is try to play with a different kind of process in order, I mean, to minimize the challenge and to learn more about how this process is going to be impacted then in the performance of hybrid electrolyte. Then we will have, I mean, that delamination in order as well to explore different of kind of pressure that as well, that depends what kind of method you use. I mean, we will learn what is the impact of the pressure from the blends, but not for other kind of a process and mixtures. So this as well is one of the bigger challenge, I would say, in hybrid electrolyte based on inorganic electrolyte. And then we are going to combine here as well operando X-ray methods in order to understand better the chemistries and interfaces between these two components. Machine learning as well, that is going to help us for the processing as well, or hybrid electrolyte in order to understand better the effects of the pressures and this whole mixture that we are going to use it. Yeah, then we'll have, I mean, the self-assembly, battery test, and then, no, sorry, and then, so we'll have as well the third is the anode part. So we are going to use the lithium metal. This we are going to work with the different interlayers in order to make compatible our hybrid electrolyte with the lithium metal. And it's going to be as well, we will have a modeling in order to support, I mean, what kind of interlayers they have more affinity with our hybrid electrolyte and lithium metal. Lamination, that as well, we are going to work a lot here with the operando safety analysis in order to understand better the safety mechanical impact in these anode and interfaces. And then we will do the assembly now, yes, of the cell, battery test, and recycling. That one of the things that I would like, I mean, as well to try is to recycle the materials and test again in the cell and see, I mean, how that cell can perform. This is the consortium of the seal belt. So 14 partners that I said previously. So we'll have, I mean, seven countries. So France, we'll have CNRS, EA, ILL, Blue Solutions, and Renault. So CNRS is going to be more focused on interfaces, cycling, simulation, recycling. CA is going to work more in cathode active materials and battery safety protocols. That I think as well in solid state is one of the big challenges as well, safety. So far, I mean, we are using the safety protocols for the liquid for lithium-ion batteries, but I mean, now I think for solid state is going to be very different, and it's something that we want to learn and explore more in order to have new protocols that they can fit, I mean, for these new solid state cells. ILL, so for operando X-ray and tomography imaging, Blue Solution that they have a huge expertise in lithium metal. So they are going to support from that point. Renault as a end user and battery cycling test. Then CNRN in Belgium as a current collector coatings, Imperial College London from UK from the machine learning. In Spain, so we are going to work more in general for hybrid electrolyte, UPV polymath. We are going to work in electrolyte synthesis, CAC in electrolyte in organic chemistry and charge transfer modeling. Polykey is a startup here in the Basque Country. So they are going to work more with the polymer scale up and the supplies of the polymers. And CSIC in the inorganic materials. Italy, also engineering is going to work with the life cycle assessment and eco-circularity. And in Germany, we have NEET, so it's going to work with the recycling part, and ZCW for cathode materials, coatings, and scale up. And finally, we'll have a Euro support, for the scale up of the materials. The work program of the SILBAIL is based in 10 different work packages. So we'll have, the first one is for the cells target requirements that I commented a little bit before. Electrolyte innovation is the work package 2. Then we'll have cathode development, anode interface, battery assembly, optimization, and cycling. Then safety characterization with the operando analysis, and work package 7 is for recycling methodologies, work package 8 for industrial technology development. So and then the last 2 packets are more for communication, demonstration, exploitation, and project management, the last one. So here is the Gantt chart of the seatbelt project, and so the seat project started in July of 2022. So now we are in 6 months, in the month 6, and so we have, one milestone that is more related to dissemination, exploitation, and communication. That CNRS Didier is in charge of this. And then these all start the milestones that we have through the whole project. So yeah, so that is all from my side. So thank you all of you, and I will be very happy if you have any questions to answer. Thank you.
Thank you, Irina. It was very interesting to see how you're going to tackle this in the seatbelt project, and seeing all the partners involved. I was also intrigued by the use of the machine learning that you intend to do for especially the hybrid electrolyte. Like machine learning, you always set sort of targets and then let the machine to work. What are, because there's so many indicators, and we talked about trade-offs earlier in the Astrobat project. So what is the main indicators that you want to set those machine learning algorithms towards?
So with that, what with the machine learning is in order to, I will say, to understand better and to try to minimize, the all parameters that we can play with the hybrids. If you are thinking, related to the processing, how you use, different pressure when you have to calendar, how you, I don't know, the temperature that you needed. I think, the key parameters that they have, that they can be very related. Then how you process, how your materials is going to behave, and if you have to design up to optimize. So really to have that relationship between them. I think, it's a loop that is very, I think it's very close. At the end, how depends what material you have, your process is going to change. So machine learning, I think we can help a lot with that.
Yeah. Okay, that's clear. I don't know if there are any other questions. I don't see anyone popping up in the Q&A for now. And I want to thank you a lot, Irina. I think you have a hard stop at 4, so thank you so much for joining us and giving us this insight in this project. And then we will move already. Thank you to the next project, which is the Helena project. And I think we have Pedro. Yeah, I already see him. Hi, Pedro, with us today. So Pedro Lopez Aranguren is a research associate in the group of cell and electrochemical testing at CSC Energy Gune. In the Basque Country, he received his PhD in material sciences in the Instituto de Ciencias de Materiales in Barcelona, and he worked as a postdoctoral researcher in Delft. And his research activities currently focus on the development of ceramic and ceramic polymer electrolytes, but I think the Helena has a kind of slightly different electrolyte as well, so we can see how they tackle that. So welcome, Pedro, and looking forward how the Helena project is tackling these challenges.
Yeah, thanks a lot, Wouter, and hello everyone. So I'd like to present you the project Elena that has started actually 6 months ago. This is an overview of the presentation. I would like to give you an overview of the main goal of this project. Then I will briefly mention about the concept and approach of Elena. And then I'd like to break down all the research and development challenges that we are heading with these solid-state batteries, and then how this project will try to tackle all these hurdles. No, so this is an overview of the project and the context. So this project actually falls in the same call as a seedbed project. It has also started 6 months ago in 1st of June, and it falls also on the same cluster 5 on climate, energy, and mobility. So here, the goal of the project is to support Europe on the transition towards the climate neutral continent. So we are talking about the energy and mobility in the electromobility sector in the next years. We are targeting reduction of the greenhouse emissions in all the energy and transport sectors. And so the project Elena focuses on the use of highlight solid electrolytes for both electric vehicles and as well as aircrafts. No? So we're talking about high energy and power solid-state batteries in the 4B and 4B generation batteries with lithium metal, based on nickel-rich cathode, NMC, and the lithium metal anode. And here the core material, which is the solid electrolyte. So as I was mentioning, we are targeting electric vehicle and aircraft applications. So this project is actually coordinated by CIC, and it has a length of 4 years. And well, you may already know from previous presentation from Irune that actually the goals or the KPIs for this project are shared within the same call. So we are having very ambitious KPIs in terms of energy density and cycle life. Actually here also in Elena, we are targeting very high C rate charging up to 10C with the high voltage active material. And then in terms of cell, we are starting from low TRL level, TRL of 3 cell coin cell level, and then we will increase up to TRL 5 to 6. So that means that we will start assembling small cells and pouch of around 40 milliampere hour capacity, and then step by step we will increase to 1 and 10 ampere hour cells. Of course, as part of the project, we are aiming to decrease the cost of the cells down to 75 euros a kilowatt hour. And then, of course, on the side of the recycling, we are aiming to recover most of the metals and key materials within the chemistry of the technology. This is the schematics of the solid-state battery in Elena. So we have a composite cathode, including the active material, with a specific coating to improve the stability with the solid electrolyte and the electronic conductive additive on the formulation of the cathode. A halide solid electrolyte thin separator between the cathode and then the lithium metal. To improve the compatibility of the halide with the lithium metal, we will develop artificial protective layers in order to maximize also the performance of the cell, avoiding dendrites and all these problems during the cycling. So Elena is clearly divided into 3 main phases. We are now starting in the project with the first phase on the development, optimization, and upscaling of the core materials for the technology. So here we're focusing on the 3 main materials that will be processed into components of the battery. That is the halide solid electrolyte, the cathode, active material and the lithium metal anode. So here in this phase, we are starting at a low scale, lab scale, to prepare these materials that then are tested in the subsequent phases of the project, and then within an iterative way, these materials will be optimized according to the electrochemical performance, and then finally upscaled by the partners participating in the project. So in the second phase, that takes materials developed in phase 1, we will process all the materials into those battery components. At the beginning, we will start by assembling very small cells of around 1 to 2 milliampere hours and pouch cells of small capacity. But then step by step, we will increase to larger formats and reaching the goal of the project, which is to develop 10 ampere hour cells. So actually also part of the project is to start increasing the energy density, first by starting with low active materials loading and low nickel-rich layered cathode oxides, and then step by step increasing the loading, as well as shifting to high energy density cathode. And on phase 3, there will be a lot of iterative activities on the testing, optimization and validation from previous phases. So here we start by setting all the electric vehicle and aviation requirements, not only on the cell performance, but also on the safety, according to these end user specifications. And then there will be a lot of inputs generated from the modeling activities on multi-scale and multi-physics. So here the goal is to develop a battery model that helps to provide guidelines on how to optimize those materials in phase 1, as well as optimizing the cell components. And then on the side, let's say more on the validation. So we will explore, we will try to investigate on the mechanisms of cell failure and degradation at both component and cell level. And of course, it will be developed all the recycling concepts, to recycle the components and to develop sustainability and cost models. And here I tried to break down the challenges that we are facing. I guess this is common challenges with other solid-state battery technologies. So if we analyze the challenges by the components or by materials on the cell, starting by the lithium metal anode, here we have the challenge on the reactivity of lithium metal with the halide, in this case with the solid electrolyte. So here it will be a key to develop this interlayer to improve the compatibility between both materials. But as well, we need to ensure low interfacial resistance, which is key to achieve all these fast rate capabilities of the cells. And it's also very challenging to give the step up from a small lithium metal pieces, to let's say larger areas, for the large cell formats. On the side of the solid electrolyte, there is also a lot of challenges. I would say that main one is to ensure the stability of the solid electrolyte, in membranes, in thin membranes, and the compatibility with all the processing steps towards the large-scale manufacturing. Of course, high ionic conductivity is a must if we want to target all this fast rate performance. And then in terms of the cycling, long-term cycling, of course, lithium metal is also one of the bottlenecks that we should overcome. On the side of the composite cathode, here we need to ensure stable coatings that improve the compatibility of these layer oxides with the halides. And of course, if we want to reach all these high energy, high gravimetric and volumetric energy density, we need to work at very high active material loading. So that's also part of the challenges. If we analyze a little bit more out of the materials, the processing and cell manufacturing here, I would say that all related to design and processing of the components for solid-state battery application, it's a challenge, given the fact that there is not many knowledge or expertise still developed. On the side also of the cell assembly and manufacturing, so here we need to consider also the cost of materials and all the circularity of materials and processes. Speaking about the recycling, so here it's also very challenging to be able to recycle most of the materials in the battery to reach all these European targets, and to recover the active materials elements with high efficiency, especially for cobalt, nickel, and lithium metal, and of course it will be a challenge to demonstrate the recycling of the halide electrolyte, recovering all these key or critical elements. And then finally, on the safety, it's a challenge to accomplish all the safety standards in our case for the aeronautic and electric vehicle application. So the approach of ELENA to overcome these challenges is actually part of these 3 phases that I already explained. So here you have an schematic view of the different phases taking part. So not going to spend a lot of time here, just to mention that we plan to tackle the materials challenges on phase 1. Considering all the steps on processing and optimization of the chemistry of the materials and the interfaces. Then on phase 2, we will tackle all the processing challenges. So starting by, for instance, wet coating, and then going towards more efficient and the lower cost processing, such as extrusion. And then finally developing all these prototypes, in small pouch cells that we will begin with 1 ampere-hour cells, and then step by step increase to 10 ampere-hours. So this is the main schematics of the project, and then of course we will count on having inputs from similar projects in solid-state batteries in the same topic that will help to overcome these challenges. Of course, we count on a very high value chain with the key partners in the project. Here is you can see the summary of the 15 partners taking part of the project. So on the side of the material suppliers, there are 3 key players here: Saint-Gobain, EMIRI, and Leonvolt, that will work on the core materials, halide, active material, and lithium metal. Then on the battery component and development, there will be several actors working on the cell assembly at small scale and cell performance, and evaluating the cell performance. And then when we take a step up into the large cell assembly, so there will be 3 main partners participating in the manufacturing of large pouch custom cells from Fraunhofer and CSE. On the work package of testing and aging and safety, there will be also key players participating: Austrian Institute of Technology, IFPEN, Energie Nouvelle, Aachen University, and FEB, working together with us, with CSE and Energiegune. On the side of battery modeling, we will also have 4 partners working towards optimizing and giving guidelines to the project. So IFPEN again, Fraunhofer, AIT, and CSE. And then on the side of the recycling, LCOS and LCA, there will be Mimitech along with Zavala. And finally, we have 3 end users for the project on the aircraft and electric vehicle applications, FEV, Pipistrel, and Leonardo. So all these partners will contribute to the project to hopefully address all the challenges. And finally, I would like to finish with this link to the website. If you want to know more about any news, results, and events, you can always have a look into the website. Thank you very much.
Thank you, Pedro. It was very interesting to see what you're doing here in this project. So if you have a question, and there's already one popping up, to Pedro, just please leave it in the Q&A. The first question is, what is your approach to tackling the high sensitivity of the halide electrolytes during production?
Okay, so yeah, that's a very pertinent question, because halides are very sensitive to moisture, similar to other materials such as sulfides. So here we plan to work on the composition of the halides in order to improve the sensitivity of the material towards moisture, to be able to handle in dry conditions, in the dry atmosphere.
Yeah. Also in the overview, so you're already looking at the requirements coming from the aviation sector. Is there very specific indicators requirements which you now need to tackle on the material level as well, or is it mostly are there any specifics that you now need to change because of the aviation requirements?
Yeah, specification of the aviation application falls mostly on the technical requirements in terms of charging, operating temperature, and so on. Mm-hmm. Less on the material side.
Yeah. Okay. So it's just the final project. Yeah. Okay. Safety. Yeah. So you with the planning that you had for the material side, you can still go ahead and meet those requirements.
Yeah, that's right.
Okay. In case if there's no other questions, I like to thank you now, Pedro, for this introduction, and I want to also invite the other speakers who have just presented the projects to join us again. So we have unfortunately Bruno had to step away, and also I just got a message from Martin, who had something popping up, so who cannot join us. But if we look at all the projects, and we have seen very similar challenges so far. Is this just the challenges that we need to tackle, and which of those? So we talked a lot about the electrolyte. Is that the main challenge? I don't know, Robert, if you want to comment on those. So, like, in terms of anode electrolytes, cathode, what are the main parts that we really need to fix before we can take the next step?
Yeah, it's a good question, and I think there is not only single answer on that. I think it depends on the approach, and yeah, groups that have better experience than my group are working for a longer time on these topics, using different approaches, different ceramic electrolytes or polymer electrolytes. All of them, there is one common thing that actually KPIs that we have at European level are too demanding and too optimistic, and it might be maybe reachable that we need to go back and design material which has slightly different properties compared to the material that we use for liquid-based cells. So now, what will be the winning combination? I think there is still a lot of ongoing work on polymers, on solid electrolytes. We saw the last presentation on halides. That's actually still, I think we still didn't explore the complete area of possible combinations, and there is still a lot of room for the improvements, and I think that should be tackled by European Commission as well. But then when we go to the production, as we saw from some presentations rely on the already some ongoing processes which are different to the current processes for lithium-ion liquid-based cells. In last presentation, Helena presentation, actually we heard about problem with highlight electrolytes, so requires really pure atmosphere without almost no humidity. So that's another problem. But as I said, there is a not unique solution. What actually we need to be aware that we need to be unique on the lithium metal side, which has to be thin as possible, but also protected, additionally protected, since we see dendrite growths whatever we do.
Okay, that's a clear recommendation there. To tie into this, today the work program for 23 and 24 for the BET4EU was pre-published. So the latest draft from 8 November was published just while we had this session. And I think one call there is tackling lithium metal, thin lithium metal production. So that's definitely been something that's being worked up so far. From the points that you just said, if we don't look at this specific parts of the battery, but at the specific challenges that were mentioned, I don't know. A lot of the things I saw back was also the how to deal with the high loading or get the high loading for the on the cathode side. Nicola, is that a specific challenge that you also see, or is that something that we sort of get to tackle now in these projects and not need to expand anything further on?
No, I think it's a general challenge. I mean, we have been dealing with that, and as I pointed before, by increasing the cathode loading at a parity of C rate, you increase the current density, and then if you have lithium metal anode, then you increase the probability of having a short circuit yeah. So, and you decrease the cyclability. So it's a problem. It's a problem that most of the scientific literature doesn't really tackle this issue, because most of the studies, like the vast majority of the studies that we encounter, they use loadings that are really not relevant. So that when the loading is below 1 milliampere hour per square centimeter, I mean, this is not even high power. I mean, this is really nothing to do. And if we want to go to high energy density, then we have to use over 3 milliampere hour per square centimeter, and this is really difficult.
Yeah. So again, here we have to have different indicators to juggle with, and we have to make trade-offs. In that case, Guinevere, you were talking a lot about trade-offs as well in your presentation, but that was more on the printability side. How do you see this challenge going forward? How can we do these trade-offs always going to be trade-offs, or can we advance in a way that we get the results that we want without having to trade something away?
I think to a certain extent we're always going to have trade-offs. As we mentioned before, it's just a matter of which trade-offs we're willing to accept and which not. I mean, maybe we manage to accept the trade-off in terms of, that we get a good processing method with a good energy density, or things like this, but maybe we will end up making trade-offs in terms of, okay, which elements are we willing to have in the cell versus what performance do we get? I mean, if you're looking at some of the various solid state electrolytes, there's elements in them that are on the EU critical list. Is that something we can accept, and where are we willing to make the trade-off? And so I think it's going to be simply a matter of which trade-offs are acceptable for us and which ones are not acceptable for us. And the ones that are probably not going to be acceptable are in terms of, extremely high production costs, in terms of energy density or power density and things like that. These are going to be the main things that are going to come to the forefront, and then which other trade-offs are acceptable.
Yeah, in your presentation, you also made notice of the eco design approach, and also taking into the sustainability parameters. That's another thing to juggle with. Do you expect something to come out from that in a way that you will reflect differently on the procedures you have used so far, or are you quite optimistic that the approach you have taken will also do well on these sustainability parameters?
There are certain aspects where it certainly has helped us in terms of evaluating which processes are the most interesting. I think we've seen with the last couple of presentations that there's a move towards extrusion-like or solventless processes. This is also an aspect where you can go through and do an LCA or an eco-design approach. Here, if you manage to avoid the drying steps, then that's already a gain in terms of CO2 production, in terms of energy consumption, solvent recovery, and things like this. There's certain aspects that we're certainly looking at that may be integrated towards the end of our project that is still ongoing, so I can't really talk about them yet. But there's certainly things where that's going to guide us.
Okay. So yeah, it is indeed one of the leading indicators that you also steer upon and use to go. Another question coming in the Q&A is also about trade-offs, or compromises it's called here, in terms of performance of the battery towards move towards faster commercialization, because there's a lot of research still to be done. I think that's very clear from all the presentations. On the other hand, there is this demand to push things toward application. How do you? I see Robert is already has typed an answer, but do you see any especially since you're working towards working with Blue Solutions on this? Do you see different indicators being asked from them, or different trade-offs to be made?
Yeah, when we discussed all the KPIs, actually there was a big concern whether they are reachable or not. So in the proposal, actually we designed that so that we differentiate between the room temperature behavior and maybe behavior at elevated temperature, where we know that polymer electrolytes or all these solid state electrolytes have reasonable good conductivity, that also these KPIs might be reached. So that's our mitigation strategy to reach everything.
Okay. Let's see, Pedro, how are you looking at this in your project, since it also has this industrial side? You have an industrial end users on board. Do you also have this kind of mitigation strategies to make a trade-off for what's useful for industry to industrialize to the next step and whatnot?
So we are not at that stage yet, but what I would say is that I mean, in general, for solid state battery, it's something that also Nicola was pointing out, that it may be not so difficult, let's say, to make small demonstrators at low loadings, below 1 million per hour per square centimeter, and in coin cell format or Schweizerloh format, but then taking the step forward, the step ahead, not towards, let's say, pouch cell concept, it's a completely different thing. So I mean, in Elena, we will have to see how can we make this step. So far, I believe is the main constraint of the solid state battery. We see a lot of performance in small devices, but not so far many results with really thin solid electrolyte separators, with 50 or below microns, and high loading cathodes with lithium metal. So that's still, I guess, the thing to accomplish.
Okay, yeah, that's one of the key challenges. I think also in scale up, indeed, is one of the to come back to the recently published work program. One of the 2023 calls will try to push things to a little bit higher TRL, and then can see what trade-offs then need to be made. I think also, Robert, in there, the target of the C rate is a bit more varied, so to not get the same constraints as you have already. So I think some lessons learned are already being implemented in the new work program. In terms of knowledge sharing between the different generations of European projects, I mean, Nicola and Pedro, you work both in the same institute at CIC. How do you achieve this knowledge transfer between Safely Move and Helena, and is there any that you could really profit from?
Well, I don't know if Pedro, maybe you want to answer about this.
Well, it's true that, I mean, there's a shift now between both projects, because I believe Safely Move has been, it's 2.5 years now since it started. So I mean, they're on different status progress, and chemistry is different, but I believe that especially on the side of the manufacturing or even the lithium metal, because that's really we share these common challenges. So I hope that we can leverage some of this development that Safely Move has already maybe or is accomplishing. Maybe that can be helpful for our case. I mean, on our side, we are in Elena. We're willing to cooperate with projects within the same call to progress faster. So
let's see if we can use this as a kickoff of more cooperation to the future, and also facilitate that from the BIPA side of things, to make sure that we hold each other's hands while we are progressing, and also towards future projects. If we look, there's several different challenges, and some of them are more in the low end of TRL, other ones in the more high end towards industrialization. If I can ask Guinevere, if you look at the research, material research side, what kind of challenges do you see that you want to tackle in the future within European project? What are the challenges that we should not miss to solve?
I think some of these challenges have already been noted. Interfaces, it doesn't really matter which material is going to be key, and how to control these interfaces is going to be probably, yeah, as I said, key to make the batteries work. So when we're looking at the material aspects, of course, things like conductivity is going to be important. If you're looking at polymers, in the end, is conductivity the right measure, or is it more lithium conductivity? So really, what is the practical conductivity in terms of what C rate can you use for that particular material? I mean, aside from the issues associated, of course, with lithium and C rate. And then also long-term stability. How can these materials work not only at the beginning, also, but then over time? So I know that's not really material specific, but in the end, it's not, you can't make a good functioning cell with one single material. You have to make a good functioning cell with a combination of materials. And it's really how these materials come together that's going to be, in the end, what determines whether or not we have the technology that we have. And then, of course, the next step, how to process them.
Yeah.
We can't forget that as well.
Yeah. Okay, clear. Is anybody else wants to join in? Yeah, long-term stability. Is there some other key areas that we really need to tackle, Robert?
The question which was raised was actually also on the other side of production line. So it's manufacturability and processability, and then related CO2 consumption or emissions, and final price, which was in many projects predicted based on some assumptions before energy crisis. It's question if it's reachable now.
Yeah, exactly. The cost targets that were made are already quite challenging, and I think they only got more so both from a materials perspective and from the energy production perspective, of course. Martin went a lot into the interfaces and that we need to maybe have a really good look at them and see if we can improve there. Is that something that's worth focusing on for future programs? I mean, you have also part of looking into this in part of your program. What kind of work do we need to do there? Oh, I don't hear Pedro. But I don't know if somebody else has like a view on this, these advanced interface layers or coating materials. Is that something that we really need to look at, or Pedro has just had to leave the meeting, or is it just one aspect or just one approach, and we need to keep our eyes open?
If I can add, actually, coating is one of the key parameters for the success of Psionic project. So effective coating with the really thinnest possible coating will actually enable use of these high voltage materials, and actually bring to Blue Solution another technology which is even more affordable, or not affordable, maybe even more better for the sector that they are covering. I do believe coatings are the future, and if you want to run batteries, so this is like a preventive step, and then of course some curative steps are which will be implemented into the cells later in the later stage.
Yeah, I think that's a good point to end on. So I think a bit of the red thread throughout all this is that there are some good steps forward being made in the projects that are already going. There's some interesting challenges that are being targeted in the new batch of projects. However, we're all gonna have certain trade-offs to make, which we need to tailor to the specific application and end users, and also have many indicators to juggle, whether it's sustainability, manufacturability, or if depending on your specific manufacturing type, like printing or something else. So there's a lot of trade-offs to be made. We have interesting approaches, also including machine learning, to help us to make this these choices. So I'm really looking forward to see how all these projects will progress in the upcoming months. And I definitely invite you to when you have interesting results to share, to join us in the Batteries Europe and BEPA working groups to share them and show where the current state of play is and what we still need to put into the work programs to make significant steps. So I want to thank you all for presenting your projects today. And then I want to hand it over to Fabrice and Javier as the chair of the batteries working group in EMIRI for some final takeaways. So Fabrice.
I will leave it first to Javier.
Javier.
Okay, thank you, Fabrice. So just brief note on today's talk. First, I would like to thank EMIRI and BEPA for organizing this interesting tech talk, and to all the speakers during the morning and the afternoon session. It has been a very comprehensive one-day conference on solid-state batteries, both from the industrial and research perspective. I believe covering the full value in the industrial battery chains, from raw materials, battery grade components, cell design, manufacturers, up to application. I think it's been very, very comprehensive. It's been interesting for me to see how the main market expectations and research challenges outlined during the industrial speakers during the morning have been well covered by the research topic facing the European project presented during the afternoon. And I would like to name some of them. We all agree on the need to improve performance on the solid state technology, having higher C rate, increasing life expectancy, solving safety issues, reducing the cost, both at material and process level, but not forgetting that we are in competition with the existing liquid electrolyte lithium technology, which is our competition. We have interestingly seen that the three main materials presented this morning for the challenge of the solid electrolyte, namely oxides, sulfides, and polymers, are already covered in some of the interesting projects that we have learned today, Safely Mood, Elena, Psionic. It is interesting that we have also given a lot of importance on one of the messages of this morning to look at the holistically look at the problem, not thinking in getting the best performance of one single material, but look at the possibility of having hybrid new concept of either electrolytes or electrodes or interfaces or cell designs, as a mean to find the best of each component, as has also been represented. I think this is a line of work that we should continue looking forward, because probably the solution is on finding creative combination of materials and designs. It is clear that new, greener, and cheaper process as a mean to reduce cost and CO2 footprint is also taken into consideration in the project that we have learned today. We might be far from industrial reality when we look at the project, but this is something that at least we are looking at. System integration requirements are also considered at the application level in most of the projects. We might be far from some of the applications challenging KPIs in aeronautics and some of the project, but at least we are looking at them. It is also very interesting to see that the whole value chain is well represented, from material cell research and final uses, both in the industrial presentation in the morning and in the European project. And it's very good news that main industrial players are getting compromised to participate in the research project. Otherwise, we might be inventing nonsense things. And I think also very important, and was also identified from the very beginning in Batteries Europe, we need to challenge the different specific application requirements, from electric vehicles, waterborne, aeronautics, and we see that somehow we have seen a little bit of most of them in the project presented this afternoon. And of course, all the time the safety issue has been discussed in all the project, and both driven by cell design and by materials. Just to summarize, I think that we in Europe should follow up with this industrial research cooperation win-win route to leverage our innovation advantage to, I would say, not maintain, but gain competitiveness in the batteries industry. This is maybe one summary of takeaways of this afternoon session. And thank you very much for the opportunity.
Thank you, Javier. Fabrice, What were your takeaways?
I need to be able to read myself because my handwriting is very bad, but I will try to. So basically, I have learned a lot today, be it in the morning or in the afternoon with different angles, of course. Morning was more short-term, mid-term, and the afternoon more mid-term, long-term. So thanks a lot to all the presenters for the nice information. Yeah, the SSB topic is very active. There are many technological choices as we have seen. So there was a lot of different approaches maybe to the different projects. But I see still a strong alignment in identifying the challenges. Maybe the solutions are different, but the challenges, I think that they are well understood and they are well isolated. If you want to make an athletic comparison, I think it's a sprint and a marathon, because we talked in the morning about semi-solid. Of course, afterwards we talked about completely solid or totally solid. You have the sprint and you have the marathon. So that means that we will need a lot of funding for a long period of time. That's my request to the funding authorities, whether they are European or member states or regional. Solid state battery will be on the roadmap for many years to come. So you need stability and ambitious funding. What I also realize is that it's all about chemistry. It's all about advanced materials. So we really need to make sure that we don't look too fast about that, and it's where the focus should be. What I have also seen in the different projects is that there is a quite systematic approach to considering materials, and that would be a mistake to only look at one material and not looking at the holistic and systematic combination of the materials. So that's quite good. And some projects are already considering non-EV applications as target markets. So that's good to see that some projects are having different approach as well. Another point that I want to stress, and it's easy to say, but I think it's important to take into account from the beginning issues such as safety, scalability and manufacturability, and of course, sustainability. Sustainability can be seen on the CO2 footprint side, so going towards processes that require less energy, but also on the toxicity level, going towards processes that require less toxic materials to be used, or that can be used in a safe way. That's a little bit what I wanted to say. What I didn't see a lot is elements of modeling and artificial intelligence and machine learning. I know that there's a lot happening in Europe and in Asia on that topic. I didn't see it so much into the presentations today, but I know there's a lot happening. And if I would like to close on circularity. I think that it's very important to consider it from the start, but to consider it in the right sequence. And so you would start with repurposing. That means to try to repair. And I was happy to learn from Robert that they have this approach looking at lithium anode to try to see if there's something that can be improved in order to reuse. Then, of course, there is second life, which is for another application. Dismantling, that's always very important to make sure that when you come up, maybe not in the European project, but at the industrial side, when you come up with a pack, that this pack is going to be easy to dismantle and not make the life of the recycler too much of a problem. And last but not least, it's about recycling. And there, I think it's important to stress the challenge that recycling should always be taken into account when coming up with new chemistries, because you want to make sure that you will not have too many toxic elements or toxic problems that would make the recycling difficult. But at the same time, and that's an important element when we look at cheap composition, is that the cheaper the composition, the less incentive there will be to recycle, because the recycler needs to make a living out of it. And so these are these two elements that you will have to juggle with as you look at the recyclability of solid-state batteries as they are being developed. And so that would be my last point. No, maybe one last, and then I give the floor to Walter to close, is that we have a vibrant ecosystem of Batteries Europe and BEPA. For those of you who may not be active yet in it, my invitation is that you join us, because this is the place where you can shape the future calls that will be used by your labs. So if there is a place that you should play, it should be also in that place. And I want to thank you for that.
Thank you, Javier and Fabrice for these takeaways. Yes, again, everybody very welcome to join the process of Batteries Europe and BEPA to really establish what we where we are, where we need to go, and how we're gonna get there, and what kind of funding is needed for it. Especially on this topic, it's very good to have all the views, both from research and from industry in there. We see that especially the hopes are high. So there's a strong push to have everything at the same time. So no trade-offs. We need to, as Robert said, match all the KPIs all at once. So we need as much input as we need to see how we can get there and actually in which phases or how to go. So I want to thank EMIRI for taking the initiative of this tech talk and doing all the organization. Especially Philippe and Gemma and Fabrice, who have been working around the clock to make this happen. I want to thank everybody of you who has stayed all the way until the very end, and hope it was interesting throughout the day with the different perspectives. So thank you so much, and hope to see you soon, either within EMIRI or in BEPA context. Have a good afternoon, everybody.
Bye.
Thank you.
Bye-bye.
Thank you very much. Bye.
Bye. Thanks.